Hello, everyone. I'm audible. Okay, so fine, guys. I think I'm audible. Good evening, everyone. So I'm good. Yeah, thank you. So fine. Let's try to start with the class, guys, and let's see. So what we can discuss in our today's class. Okay. So yesterday I was talking about like a clustering problem, right? And we have seen this algorithm like a k-mean. We have seen basically H3 clustering, which is a part of agglomerative clustering, and we have seen a DB scan as well, right? So these are the algorithm that we have discussed so far, so forth in terms of a clustering. And we all know that clustering is basically a unsupervised approach. So we can try to do one thing. So we can try to like group a data set, and based out of that, so maybe we can try to perform a different kind of a operation. That is completely fine, right? So that is completely fine. But let's suppose if I am able to build a model, right? Let's suppose if I am able to build this DBS scan model. Let's suppose if I'm able to build maybe a k-mean model or maybe a S3 clustering model, I'm able to build. But the problem is how I will be able to validate, how I will be able to evaluate. Because in case of a regression, in case of a classification, as it is a supervised approach, right? Supervised machine learning approach. So it's very easy to test, or it is very easy to find out and score of a particular model, that okay, so maybe this is a training accuracy, this is a testing accuracy, because y will be a known values, and then you can try to get a y hat, which can be a predicted one, and then you can try to perform these kind of operations. You will get to know what is the score. So out of 100, so what is the total number of correct classification, or maybe incorrect classification, or maybe in terms of a regression, so how far it is in terms of a residual. So these things are pretty much possible in case of regression, in case of a classification. But what about clustering? Because in clustering, we do not have any kind of predefined y value, right? Yes, if we are going to place our data set in a respective cluster, so for sure a data label you will be able to get, data label you will be able to see that okay, so row number one belongs to cluster number one, row number two belongs to cluster number one, row number three belongs to cluster number four. So these kind of labels you all will be able to see. That is not a problem at all. But how you will be able to validate that how strong your cluster is, right? Because you are trying to bring a similar kind of a data set together. This is the meaning of a clustering algorithm, right? A very simple meaning of a clustering algorithm is, so we are trying to bring us all the data set, or maybe a similar nature of an object all together, so that it will be, or so that I will be able to perform certain operations on top of it. So this is something which happens with respect to a clustering algorithm. That's completely fine. But what is a value, what is evaluation matrices that I can try to pick and choose, by which those matrices can tell me that okay, so this is basically uh, this is basically accuracy of this cluster. So maybe you can try to increase accuracy. Increasing an accuracy means what? So increasing an accuracy means, so you are trying to create a groups in such a way that that group will be best possible, like a grouping of the nearby objects. This is something that we all are supposed to do. So fine, to validate a clusters, right? Different clusters. So there are not only just a one single approach which you can use. There are multiple approaches that we can use. And again, in interview, so whatever I'm going to discuss in next 30 minutes, so people are going to ask you questions as a questions directly in an interview, right? So how do we validate a cluster, or how do we do a validation in case of a unsupervised learning approach? Basically, it's a clustering, right? So there are multiple ways, right? So there are multiple ways by which you will be able to perform these operations. A validation of the cluster operations you will be able to perform. Because whenever you are trying to create a cluster, so for sure it is supposed to be created in such a way that it must be having a very high interclass similarity. Interclass similarity means like a similar kind of a data it is supposed to place together, and very low intra-caste similarity, right? Or intra-class similarity. So like a very on a very low level, for a very few data it is supposed to make a mistake, so where it is not able to classify, or it is not able to cluster, or it is not able to group a data set, right? So this is something that we are supposed to keep always in our mind. So whenever we are talking about like a valuation or validation of a cluster, so there may be a external entity, or there will be a internal, different kind of a validations we may try to opt for. So one of those matrices is called as rand indexes, or it's called as Jaccarddian coefficient or Jaccard coefficient, right? So let's try to understand that what is the meaning of this rand indexes. So first of all, I will write down a formula over here. So rand index, right? So this rand index is nothing but total agree divided by total disagree, or you can say in total, right? Total agree plus total disagree, right? So this is something called as rand indexes, and this is one of the matrices that we can use to evaluate a cluster at any point of a time. Apart from this rand indexes, there is something called as Jaccard coefficient. We can try to use Jaccard coefficient to perform a similar kind of operation. Apart from this, there is something called as entropy. There is something called as purity that we can try to use to perform a exact similar kind of operations. Apart from that, so there is something called as Silhouette coefficient you will be able to find out. So Silhouette coefficient is again a matrices by which I will be able to monitor, or I will be able to observe a robustness of a cluster. So it's not just one, it's many matrices that we can try to use. And with the help of that, we will be able to evaluate our cluster. So this is something that we will try to understand. And when someone is going to ask you that how you evaluate your cluster, so you are supposed to say these things straightforward that, okay, so these are the way, these are the 4 to 5 ways I know by which I try to evaluate my cluster. Entropy, purity, Silhouette coefficient, right? So all of these things we can try to use. These are like a 5 matrices. Again, there are other matrices as like also you will be able to find out, right? So there is something called as a cohesion and separations. So yeah, those things are there. So those things we can like try to use it, cohesion and separation. So these are the things that we can use to perform an evaluation of a cluster. So let's try to understand one by one each and everything. So first of all, we can try to understand basically this rand indexes. So rand indexes is one of the matrices by which you will be able to observe, or you will be able to monitor how good your cluster creation is. So here, in case of a rand indexes, you will be able to find out a couple of points. So there is something called as SS, there is something called as DD, there is something called as SD, and there is something called as DS. So what is the meaning of this SS, right? So let's try to understand this particular part, and then again I'll come back to a rand indexes. So here SS simply means that both the points belongs to a same cluster for both our algorithm and a ground truth. So here what happens is, so whenever you are trying to build a cluster, right? And whenever you are trying to evaluate a cluster, so we always try to keep or create some of the data, or we say some of the ground truth we try to create. So generally what happens is sometime your client is going to give you those ground truth, right? Maybe a labeled data set for a cluster, or they will tell you a hint saying that, okay, fine, so this is the data set that I have, and then uh, ideally this data set should belongs to this place and this data set should belongs to that places. In the similar way, like a salesman, so if salesman is going to join on a very first day, so for sure he is going to get some training that, okay, so you are supposed to manage that particular corner, in that corner, so this things is kept. So now salesman is aware about it, right? So if some other person or maybe some customers or maybe some other person is going to make a mistake, and if they are going to keep shoes or maybe a shirt somewhere else, right, in some other section, so what they will do is they will try to bring again back to the particular section, right? So in the similar way, what happens is, so whenever we try to build a machine learning algorithm, so here in terms of a clustering, so we always try to prepare our own ground truth. So ground truth simply means that a base with which I will be able to compare. So here, if a point like so let's suppose if I'm trying to put up some of the points into a cluster, right? Or I'm trying to create a cluster and there is a point which is available over here, there is a point which is available over here, and there is a point which I'm supposed to keep inside this particular circle, right? These are the new points which is waiting for maybe like to get into one of these cluster, one of like a such kind of a cluster. These points are just waiting. So here, let's suppose if I'm going to place this one over here, and again, if I'm aware about the expectations that, okay, so this should go here itself, it should not go here. So if I'm aware about a ground truth for some of the sample data set, we do prepare those things. So both the point belongs to a same cluster for both our algorithm and a ground truth. In that case, it will be 1. So SS is equal to 1 in that case. And then let's suppose there is something called as a DD. So if I'm going to like consider that. So DD is nothing but, so both point if don't belong to the same cluster, but both our algorithm and the ground truth. So in that case, it is going to be a DD or agree condition. So both the point don't belong to the same cluster for both our algorithm and our ground truth. So let's suppose if I have a points and yes, in our ground truth, right? So that point inside our ground truth doesn't belongs to a particular section or particular cluster, and even for our cluster, so it is not belongs to like a particular respective clusters or groups. So in that case, we can say that it's a DD, and then it's a 0, you can say. And let's suppose for there is something called as SD. So it's, you will be able to find out that it's just like confusion matrices that we are trying to create over here. So soon you are going to realize that I'm just talking about a confusion matrix kind of a things. So I'm talking about like false positive, false negative, true positive, and a true negative. So this is something which I'm trying to discuss over here. Nothing else apart from this one I'm trying to discuss in this particular place. So SSDD and like SD over here. Yeah. So SSDD, SD, so these are the calculations that we are going to perform, and based on that, so we can try to we can try to just evaluate that, okay, fine, so what is the total score that we all are able to get. So I'll just show you these things in a simple way. So just in a confusion matrix way, I'm going to show you. So let's suppose I have my original data, right? And here original data says that it's 1 and 0, means original data says that it will belongs to a cluster, it will not belongs to a cluster. Just imagine in this way. And my ground truth data says that again the same thing, 1 and 0, right? So if my prediction, this is, let's suppose this is a prediction from the clustering, prediction from clustering, and this is nothing but my ground truth. This is nothing but my ground truth. So this is the prediction which I am able to get from the clustering, and this is something called as ground truth. So let's suppose it is telling me that, okay, fine. So prediction wise, it is 1, right? And even ground truth wise, it is 1. Means prediction wise 1 means it belongs to one of the cluster. And even this one is saying the same thing, that yes, it belongs to a same cluster, right? So in that case, SS, let's suppose this is S, this is S. So SS, right? SD. Maybe you can try to denote SD, SD, right? This is what I was trying to denote over here, nothing else. Let's suppose your ground truth is saying that it doesn't belongs, right? But your prediction is saying that no, it doesn't belong to this cluster, but your ground truth is saying that no, it belongs to a cluster. So in that case, SD. If your ground truth is saying that it doesn't belong to a cluster, but if your prediction is saying that yes, it belongs to a cluster, a particular cluster, right? So in that case, it will be DS. And here your ground truth is saying that your cluster data doesn't belong to a cluster, and your ground truth is saying the same thing, and prediction is saying the same thing. So in that case, it will be DD. So it's just a notation that we are trying to use over here. And in that case, a rand indexes is nothing but, right? So rand indexes is nothing but it is going to be SSDD, right? Again, just as an accuracy, we are trying to do this calculation. So SS plus DS plus SD plus D. Excuse me. Yeah. So this is something that you will be able to find out in case of a rand indexes, and which is exactly same, right? Exactly same as a confusion matrices. The only differences you will be able to find out over here is in case of a confusion matrices, right? Your Y will be given. So here our ground truth will be given. So again, our ground truth is equivalent to a Y. And what is ground truth? Those who are confused. So ground truth is nothing but simple, I would say, an actual observation. So let's suppose if manually I'm trying to perform this kind of operations. So in that case, yes, that is something which I can try to assume, or that is something called as ground truth, which will be prepared by us. A cooked up data, you can say. It's called as ground truth data set. Now, Jacobian coefficient, right? So the second one is called as Jacobian coefficient. So Jacobian coefficient is nothing but so a total data set which your cluster is able to classify, cluster is able to group, or cluster is able to separate, plus from a ground truth, same values you are able to get. So Jacobian coefficient, if I'll say JC, JC is nothing but this Jacobian coefficient. So it is SS divided by SS plus SD plus DS. So this is something called as Jacobian coefficient, right? SS divided by SS plus SD plus DS. So SS plus SD plus DS. And this is how. So here we don't consider a case so where we are not having any kind of a data set in our ground truth, and even our data even our clustering algorithm is not able to predict. So apart from this, or except this, we try to consider each and everything, right? So Jacobian coefficient score we try to calculate, and based on that, so we try to validate what is the accuracy of a particular cluster, or what we are able to achieve out of this one. So this something happens in case of your rand indexes, and in case of your Jacobian coefficient. Now there is a another. So these are just a classification, a kind of you can say a matrices which you will be able to find out. So whether it's a Jaccard or whether it's a rand indexes. Rand indexes is exact same as a confusion matrices. There is no differences you will be able to find out at all at any point of a time. Now there is a something called as entropy, right? So our next thing which I have written over here is a entropy. So even entropy is a way by which you will be able to do a calculation. So now let's try to understand what is entropy. So I believe we have already seen this term called as entropy. We have already seen this terms called as entropy in our previous lectures. So if I'll talk about a formula, so formula wise, your entropy formula is very, very simple. So it's nothing but entropy is equals to minus of pi log of pi. This is something called as entropy, right? So minus of pi log of pi, this is something called as entropy. And entropy always try to tell me that how random my distributions are. This is something that always you will be able to find out at any point of a time, right? So again, same calculation we can try to establish, right, for even a clustering algorithm. So for each and every object which we are trying to place in a particular cluster, so we can try to find out a probability, that probability of occurrence of a particular object in a particular cluster. And if we are going to find out a summation of it, if we are able to find out a summation of it, or I can try to rewrite my formula summation of like pi log of pi, if we are able to find out, so in that case, right, so in that case we can say that okay, fine, so I'm able to like calculate a randomness of a data set or a scatteredness of the data set throughout the cluster. And this something is been represented by a entropy, and it's the same one that we have already discussed in our decision tree. Here we are just trying to use it uh, in terms of just our evaluation. So if entropy of one cluster is high as compared to an entropy of another cluster, in that way we can say that okay, so one cluster is bad as compared to another cluster, because we are always looking for a less randomness into our data distribution. So this is where entropy comes into a picture. Now, so there is another thing that we can talk about called as purity. So purity is another matrices. So entropy is an old one. So there is something called as purity. Now, what is this purity and how I will be able to like use it, or what kind of a matrices I will be able to find out. So purity is nothing but it's a total percentage of data set or a data points clustered correctly. Again, meaning of others are again the same. So purity is nothing but what is the total percentage of the data set we are able to place correctly inside our cluster or inside a respective groups. This is something called as the purity of the cluster. So purity of any cluster I, purity of cluster I can be defined by, right? So let's suppose pi is a purity term. So it's a maximum of probability of ij. So where ij is nothing but, so you are trying to place ith data into a jth or ith class into a jth cluster or vice versa. So this is something called as a purity. So this is just for one of the cluster you will be able to find out. Now for an entire cluster, if we have to find out a purity, so it's nothing but it's a summation of just for one single cluster. So if I'm talking about a purity of a whole cluster, so in that way it is nothing but n into pi. So this is something called as a purity matrices. Now, so so far so forth, purity matrices is not implemented inside your scikit-learn packages, but you will be able to do a calculation by yourself, right? And when we are going to see our practical example of this clustering algorithm, so we are going to find out a purity score, but by using our own method we are going to find out a purity score in this particular place. So it's nothing but just how many total percentage of the data set we are trying to find out, right? So let's suppose if 80% of the data set is correctly placed in one of the cluster, then 0.8, then 60% of the data set is placed correctly in the other cluster, then 70% of the data set is placed correctly in another cluster, right? So pi is representing what? So pi is representing a maximum percentage for the ith cluster for jth class, right? So in the similar way, so if I have to find out this entire things for the whole data set, right, for whole like a data set at any point of a time. So in that case, I can try to calculate summation of m by n pi. So where n is nothing but a total number of records, pi is nothing but a purity of a ith cluster, right? And m is nothing but your simple like a coefficient, so which is trying to represent basically a relationship between purity. So this is something that we can try to calculate, and yeah, so we can try to write our own formula by which I will be able to calculate this entire things by ourselves. So that is like a pretty much possible. Okay. Now, so apart from this purity, apart from this entropy, so there is something called as a Silhouette score, right? So Silhouette score is again one of the way by which you will be able to find out what is an accuracy of a particular cluster. So let's try to understand this Silhouette score. Or you can say Silhouette coefficient, anything is fine, right? Silhouette score. So what is this Silhouette score? So if formula wise, if I'll say, so Silhouette score S of x is nothing but B of x minus A of x divided by maximum of A of x or B of x. So this is something called a Silhouette score. Now, what is this A of x and what is this B of x? So A of x is nothing but it's an average distance of data set from all the other point in the same cluster. This is something called as A of x. So this one is nothing but A of x is nothing but it's a average distance of x from all the other points in the same cluster, and B of x over here is nothing but it's an average distance of x from all the points other cluster. Now, so just try to understand how Silhouette score is different as compared to the previous method that we were using, whether it's a purity, entropy, or maybe rand indexes, or maybe a Jacobian coefficient. So here we have to prepare our like a test data set, or we have to prepare our ground truth data set. If I have to evaluate maybe a rand indexes or maybe a Jacobian coefficient or maybe entropy or maybe a purity, unless and until I'm not preparing my data set by myself, so I will not be able to evaluate my entire cluster. I will not be able to tell you that what is the score of the cluster. So that is completely fine. But if you will look into the Silhouette score, what Silhouette score says? Silhouette score says that B of x minus A of x divided by maximum of either. So maximum of A or B. Fine. And what is this A? So A is trying to tell me that it's an average distance of a data set, right? From all the other point in the same cluster. So let's suppose if I have already created a particular cluster. So let's suppose these two clusters has been created, and inside these two clusters, I have some sort of a data. So I have some sort of a data set inside these two clusters, and these are the two things which I have already created. Then what will happen, right? So then we are going to calculate first of all A of x. And what is A of x? The average distance of so x from all the other point in the same cluster. So let's suppose if I would like to know that whether this point is clustered correctly or not, right? Whether this point is clustered correctly or not. So how we will be able to do that? So here we are going to calculate an average distance. So distance, I think we all know how we can calculate. In this way, we can try to calculate our distances, right, with respect to all the data sets. So average distance, again, we can try to calculate. So average distance of X for sure. Let's suppose this is one of the data set for which we are trying to perform this operation. So average distance of a data set from all the other point in the same cluster, right? So this distance, this distance, this distance, this distance, this distance, this distance, average of it, right? So first of all, summation divided by the total number of the distances. And that is going to give you what? That is going to give you basically A of X for you, right? So by distance means Euclidean distances, right? Yes, it's always Euclidean distances, you can assume. So whenever I'm talking about the distances, not a Hamming or not a Manhattan distances. So yeah, Euclidean distances between two coordinates, yeah, at any point of a time. So here we are trying to calculate what? So we are trying to calculate an average distances inside the cluster. That is one thing. So let's suppose I have like a 5 points. So again, we will try to calculate distance of every point, right? Every point. So let's suppose I have a 5 points. So yes, 5 average distances I will have to calculate. Then B of X. So B of X says that average distance of X from all the other points. So I have considered this as an X. So average distance of X from all the other point in other clusters. So distance with this, distance with this, distance with this, distance with this, distance with this. So average of these distances I will try to calculate, and that is going to be a B of X, right? Why we are doing it? Just try to understand this intuition over here. So see, if this one and this one is close to each other, right? This one and this one is close to each other. So can I say that that difference will be approximately close to 0? Yeah, difference will be approximately close to 0 at any point of a time. And it will give you a kind of a what point? It will give you that, okay, fine. So maybe your data sets are too close and maybe you have created a wrong cluster. So can I say that your accuracy or your Silhouette score or Silhouette coefficient will be very, very less in that case? Yeah. So your Silhouette score is going to be very, very less if it is coming closer to 0. Agree, everyone? Yes. So when this is going to give you a maximum, so can I say that it is going to give you a maximum, right? It is going to give you a maximum. So once B of X will be very, very high and A of X will be very, very less. So can I say that only in that situation we can assume that it has created a best possible cluster? Yes. So it has created a best possible cluster. So we are looking for that kind of values, and we are trying to divide by a maximum at any point of a time. So if it is maximum, so it's kind of a 0 to 1 range we are trying to create. So maximum of either of these two. So by which we are trying to divide it. So just try to understand. This is not a very new things that we are trying to understand. So mathematically, if you will try to understand this part, so this is exactly a same old thing we are trying to understand, a distance based, right? So based on the distances, so we are just trying to check what is the accuracy of my clusters over here without even using some external pre-prepared data set. In all the other examples, so we were like, we had to prepare basically a ground truth data, and then only I will be able to calculate basically a like a accuracy or maybe like a stability of my model in terms of clustering. But in case of a Silhouette, so that is not required because it is following a distance based approach to evaluate whether my cluster is a good one or whether my cluster is a bad one, right? So this is something that you will be able to calculate for what? Only 1 point X, right? Likewise, I have so many points over here. Likewise, I have so many points over here. So you will try to do a calculation for everyone. So it is going to be summation of S of X, right? 1 by total number of the record, and that is called as Silhouette coefficient. A very simple one. Is it making sense to all of you? Yes. Denominator will be higher than the resultant will be less. See, here denominator is higher simply means that like a resultant will be in between 0 to 1. So you will be able to get a result in a decimal point, and in a later stage you can try to convert those things into a average or maybe like a percentile. Simple. So which matrix is mostly used? All of these matrices are like just given to you to evaluate the matrices. So it depends upon me and you, which matrices I know and I'm going to use it. Like DBS scan, this method is a self-reliant, it seems. Yes. So for a synout coefficient, the whole data set or one cluster. So I'm talking about the whole data set. For a whole data set, you are supposed to find out, right? Let's suppose I have a 50 data over here and 40 data over here. So for all of these data set, I will try to calculate S of X, right? That's the reason. So I have written summation over here. This is the symbol, summation. Summation simply means that starting from 1 till n. So for all the n number of data set, whether it belongs to this cluster or this cluster, we are supposed to do this kind of a calculation. Higher the synout score, better the performance. Exactly. Because higher the synout score simply means that you have a clear separation. Because why we are doing a clustering? To create a very clear separations, right? So if my synout score is less, it simply means that my B of X and A of X is closer to each other. Means distance between a data and the other points in cluster and data and other point in other cluster is almost closer, right? So it simply means that we are not able to create a complete separations over here. Here n is the number of the data set in raw record. Yeah, anywhere people are using n denominator simply means that it's a total number of record we are talking about in general. If A of X is more than B of X, then we get a negative value, which anyhow means we have a wrong cluster formed. Exactly. And that is not going to happen, right? So if that is the case, in that case, why we are even building a cluster? Because if A of X is bigger, means distance between your data and data in your cluster is bigger than a data in other clusters. So it simply means that you have a cluster inside a cluster. Can I say that? Which is not a valid criteria. If A of X is bigger than your B of X, then what is the meaning of it, right? So what is the meaning of it? So it simply means that you have a cluster inside a cluster. So there is a complete overlap we are observing, and in that case, we will not approve this one. Simple, because this is not a situation which should happen in case of a clustering. Okay, so now the score lies between 0 to 1 and above 1 as well. Now, in between 0 to 1, because we are just trying to divide these things by maximum. Just try to look into this mathematical expression. This mathematical expression itself explains you all these things, right? So it's a very, very simple, like a mathematical explanation that is given, and we'll do our calculations again. For this, there is a library available inside your scikit-learn, right? So simple, you should call like a your algorithm dot silhout underscore score, done. It will do all the calculation, same calculation, right, and give you the result. So is this things fines to all of you? Will you be able to explain Silhouette score, rand indexes, Jacardian coefficient, entropy, and maybe a purity? Can we use Silhouette score for DBS scan? Why you are even asking this question, Naveen? When I simply said that this is like a matrices which can be used for any clustering algorithm. So where is a confusion in this version? Okay, so this is all about like valuation, right? So just try to remember a couple of these things, right? I think that will be better. Still, how to score if you can explain in your interview. So I think that will be way more better, right, as compared to anything else. Now, so moving ahead with our next algorithm, and that is called as principal component analysis, right? So now let's try to understand another algorithm called as PCA, principal component analysis over here. And let's try to understand what is the meaning of a principal component analysis, why we are even doing it, why we are even learning these things. Principal component analysis. So you will always be able to find out kind of a situation. Again, principal component analysis is not a approach by which you train a model. Let me tell you one thing. Principal component analysis is one of the data pre-processing stage. So where you use a PCA, LDA, or TSNE to find out, right? So there are multiple like subordinates you will be able to find out, right, over here. So in terms of a PCA, so PCA is a kind of a algorithm, so which can be used. So which can be used for what? So which can be used for the dimensionality reduction, right? So let's try to understand how we can try to use a PCA for a dimensionality reduction. What is the meaning of dimensionality reduction? Why it is required, by the way, right? And where we can try to use it. And you will be able to find out that PCA is a very, very powerful algorithm that we can try to use in many situations, or even LDA, even TSNE, right? So these algorithms are used for basically a dimensionality reduction. So anyone who is having any idea what is a dimensionality reduction? Any idea? Eigenvalue, eigenvector, anyone who has studied in childhood? Reduce the number of the feature, reverse of kernel tricks, okay? Multiple dimension to three dimension, not only three dimension, just less. That can be any number. Reducing the actual dimension of the data set, feature selection, okay? So I'll try to explain you this PCA in very, very detail and in very, very depth so that you will be able to visualize it, right? So just try to focus for next 2 hours without any deviation. This algorithm is complex. Although this algorithm is not been used for a training purpose, it's a data pre-processing technique, right? But it's been asked heavily in your interview, right? In many of the interview, people are going to ask you, and implementation wise it's nothing, but what I do generally in PCA is, so yes, by using a library I will show you a implementation, but that will be in a last stage. But I'll show you a implementation by using a manual approach, right? So that even you will be able to decompose a data set of maybe 100 dimension into maybe 1, 2, 3, 4, 10, whatever you want, right? So in that way, I'm going to talk about this entire principal component analysis. But this one is like a math heavy operation. So just try to like a focus over here instead of asking which one is better than what. So people don't know. So see, many people ask this kind of a question, which one is better? Nothing is better or nothing is worst. I keep on saying these things, right? If I already know that, okay, fine, so this is the best one, the best algorithm, I will just learn and then I will use it and then my work will be done. Then what is the need of learning another 100 algorithm? So why even you are asking this question, which one is better and which one is worst, right? What is the need of learning a 10 classification algorithm or then 5 or 6 clustering algorithm and then like a 10 regression algorithm and then on top of that other algorithm? If I already know that, okay, fine, so this one is better. In that case, directly I will try to explain you that one, right? I will not even waste my time explaining you all the mathematics and then explaining you in terms of practicals. So just grow up, right? My only advice is grow up. Okay, so here let's try to understand what is PCA, right? So what is PCA? What is a principal component analysis and how it is going to help us out, right? In terms of reducing a dimension, or before that, what is a need of dimensionality reduction? Why even it is required? Why can't we use a data set in its original format? So let's suppose, right? So let's suppose I have given you a data set, yeah, and sit tight for next 2 hours, because 2 hours is a minimum time it is going to take just to explain you its theory and its mathematical concept, right? Bare minimum time, I'm telling you. But beyond that, PCA doesn't exist, right? Beyond this 2 hours. So this will be the end of PCA. And like I said, it's a math heavy, so I'll just go slow. Don't worry. Let's suppose, and again, I'll try to explain you in a very simple way. So I always like does that. So it's fine. X1, X2, X3, X4, X5, and so on. Let's suppose we have hundreds of columns, hundreds of features which is given to us, right? Now, so can I say that if I'm going to consider hundreds of columns, right? And then let's suppose I'm trying to find out a relationship with Y, right? Relationship with Y I'm trying to establish, or maybe just a clustering algorithm I'm trying to build. So I just have a X1, X2, X3 till X100. So if I'll try to train, or if I'll try to pass any of like a such kind of a data which is having hundreds numbers of a column to our model, so a very first thing which is going to happen is it is going to increase our time complexity. It is going to increase. Second thing, what will happen is, so it will be find difficulty. So it will be find a difficulty so to build a relations. So difficult generalize a relation, because whenever we are talking about a machine learning algorithm, it's nothing but just a generalization of the pattern of the data. So it, for sure, if we have hundreds of columns and then one Y, so if we are trying to establish a relationship between a feature and the label, right? So for sure, it will be difficult. It will be difficult in terms of generalizing these data set, and it will be difficult in terms of establishing a relation, right? So which you can say like it's a curse of dimensionality. Plus all the time, all the time, right? All of your features are not going to contribute. Right? So all the time, all of these features are not going to contribute at any point of a time, right? So for sure, I have 100 number of features, right? I don't know which one is going to contribute more, which one is going to contribute less. And for sure, 100 number of features are not going to contribute equally. That we have seen even in our linear regression algorithm. Otherwise, value of M will be same in this equation, right? So M1x1 plus M2x2 plus so on plus C. So all of these features are not going to contribute equally, right? Otherwise, value of all of these M will be same, right? Which is not the case at any point of a time. So there are so many problems we are going to face if number of feature will keep on increasing. Plus, hard to find out shape of data, right? So let's suppose if I'm talking about, right? So let's suppose if I asked you, so can you please visualize a 100-dimensional data set? So what you will do, you will simply say, no, I can't visualize it, right? Because max to max, I will be able to visualize a 3D, right? 2D, 3D, I will be able to visualize, but beyond 3D, I won't be able to visualize. So if I'll ask you, can you please tell me what is the shape of the data set? Whether it's a spherical, whether it's a rectangular, or whether it's a oval, right? You won't be able to tell me at all because your data set dimension is equals to 100. And that is a problem at any point of a time in terms of doing a visualization, because there is no such unit or libraries which exist in this planet. Like, yeah, 4D exists for sure with the help of some special opticals, but here, so beyond 3D you will not be able to visualize at any point of a time, right? So there are so many problems you are going to face when a size dimension of your data set is going to increase, right? Means number of features. I'm just talking about a number of features as of now. I'm not talking about even a number of rows. So there are so many problems I'm going to face if these things happens. So what is a solution? How I will be able to overcome all of these problems at a time, right? So a solution for that one is nothing but dimensionality reduction. But some of us thinks that dimensionality reduction is nothing but removing a column, right? Which is not true. Some people think that okay, so we have 100 number of columns, and now we are trying to like bring down these columns to a 3 or 4 or 10 or 15 out of this 100, right? So we are trying to remove some of the column, but no, dimensionality reduction you can't compare with the elimination method. So there is something called as a forward elimination and a backward, right? So dimensionality reduction is not a elimination technique, it's a reduction technique. A reduction is different, elimination is different. So here we are not eliminating our rows, sorry, columns, not rows. So here we are not eliminating our columns at any point of a time. So what we are trying to do then, right? So we are trying to, again, mark my word over here, that we are trying to convert a data set in some other axis in such a way that it will be able to retain a original meaning of a data. We'll try to understand what is the meaning of this line, right? For sure. And we'll try to prove the same thing for sure over here. So this is what we do. So we do basically a reduction over here, maybe from this 100 column. So we can try to reduce it to a 3 column, 4 column, 10 column, 15, or maybe a 20, or maybe even a 99 column, right? So that is practically possible. So how practically it is possible? So let's try to understand this particular part. So I'll give you a very small and very simple example over here, right? So let's suppose this is a coordinate system that I have, right? So this is my x1 axis and this is my x2 axis, let's suppose. Now here is a data set which is given to me. Fine. So here is a data set which is given to me. Let's suppose I'm writing a coordinate of this particular data set as, right? So I'm writing a coordinate of this particular data set as maybe 2, 2. Let's suppose I have another data set over here, right? Maybe coordinate of this data set I'm going to write as -2, -2. Let's suppose I have maybe another data set over here, and here I'm going to write down -2 or maybe -1. I can write down, right? -1, +2, right? So these are the data set, let's suppose, which is given to me over here. So just try to understand in layman way, right? These are the data set. So let's suppose x1 and x2. Fine. So x1 and x2. So 2, 2, -1, 2, -2, -2. Fine. So can I say that these are the two rows, these are the two columns that we have? We are just trying to represent those things into a coordinate geometry. Agree, everyone? We have two row, right? Sorry, again I'm saying row. We have two columns, x1 and x2, right? And we are just trying to represent these things into a coordinate geometry. This is the representation, right? This is the plot that we are trying to draw over here. Simple, right? Okay. Now if I'll ask you, can you please represent all of these data, right? Can you please represent all of this data maybe by using just one single axis, right? Just by using one single axis, can you please represent a meaning of this entire data set? So what will be your answer? Any idea? Let's suppose there are like a, with the, because see here number of axes is how many? So can I say that number of axis is 2, right? X1 and x2 is the axis, that is equal to number of the columns. This is the representation, right? So now I'm asking you, just try to represent all of these, all of your data set, right, with respect to one of the axis. Yeah. So what you will try to do, so maybe you can try to give me, okay, you will try to say that, okay, so this is a component for this axis, and it's like a -1 is a component for this one, -2 is a component of this one, right? So maybe this is the component. So component wise, so yes, for one of the axis, this is a record. For another axis, maybe this is the record that I'm able to find out. But I don't know that how to represent this value, the another axis value into this one. Can I say that this is the problem that you are going to face? Yes, this is the problem. So you don't even know actually. So let's suppose if I'll, but somehow hypothetically, just try to imagine this one, right? Just try to imagine one of the axis I'm able to represent. That is completely fine. My question was, we have a two axis x1 and x2. Just try to represent this entire data set in only one axis. Fine. Maybe I can try to do it. I can just try to attempt. But when I'm trying to attempt it, so yes, this one I can like it's already represented in terms of x1. This is already represented in terms of x1. This one already represented in terms of x1. But what about this x2, which is given to me, right? I'm not able to find out any component by which I will be able to represent this particular data set in this format, in a x1 format. But somehow, if someone is going to teach me, right, somehow someone is going to tell me that, okay, this is how you can even consider these components as a part of x1, right? So can I say that I will end up converting even x2 as a component of x1? Yes. So this is what we are supposed to find out. This is something. So this is just a hypothetical like a situation that we have as of now, right? So we'll try to understand how it is possible, how we can try to achieve it mathematically, right? But what we are trying to do over here, simple. We are trying to, we have two coordinates over here, we have two columns over here. We are just trying to represent another coordinate in terms of another coordinates. If somehow I will be able to do that, I will be more than happy, and I can try to like reduce two dimension to one dimension. So 100 dimension to any other dimension I will be able to reduce, right? So but we don't know how to do it, right? So let's try to find out an answer for the same thing. But the whole idea is to convert, or to whole idea is to represent this entire things into another format. That is the whole idea over here. So represent x2. So whatever is data set is available on our another axis in a form of one axis. So if I will be maybe on a third axis, not even x1. So maybe not even x1 or x2, maybe on some new axis, if I can represent, right? So maybe on a new axis, if I can represent x1 and x2 both, it will be well and good for me. So that new axis could be, let's suppose if we are trying to create this one, this line, right? So if I can represent this data set with on this line, this on this line, this on this line, right? Then can I say that this line is going to represent relations of both? Yeah. So someone, Nilesh, is suggesting me that x cos theta plus x sin theta. Uh, no, Nilesh, but again, so see, if you are trying to find out this x sin theta and x cos theta, right? So you are actually losing another component, because there will be, if you are considering a sine component, then cos component you are going to lose, and if you are considering cos, then you are losing a sine component. But the problem over here is we are not supposed to lose either a sine or the cosec component, right? So that we can't do. So let's try to understand what is the solution then, right? But the problem statement with this one, problem statement is very simple. So I have this two data set, right? So I have like two columns. I'm supposed to maybe convert these two things into another column, right? So another column C, so which may another column we are supposed to convert. So where it can represent the component of, or maybe whether where it can represent these both of these two data set over here. So let's try to find out, and let's start with a actual algorithm called as PCA, principal component analysis, right? So principal component analysis says that it is possible. It is possible to convert one of the component or one of the like an axis into another axis, and it is possible to derive one of the axis in as a form of another axis. So that is pretty much possible, and we all can try to do it, right? How? Let's try to understand one by one. So here is a plot that we have. So let's suppose we have x1 and we have x2 over here. And let's suppose we have a data set available over here. We have available over here. We have available over here. We have available over here. And we have available over here. So these are the data set which is available to me. So principal component says that step number one, right? Step number one, you are supposed to take a data set which is having mean is equal to 0 and standard deviation is equal to 1, right? This is what a PCA says. I'm just trying to like explain a PCA, a mathematical background of the PCA. So PCA says that okay, so at any point of a time, right? At any point of a time, so you are supposed to take a data set which is having mean is equal to 0 and standard deviation is equals to 1. So can I say that I'm actually talking about the standard scalar? Yes. Or I'm talking about a standard normal distribution, right? Okay. Now just tell me one thing. Do you think that this data set is available in a form of standard scaling? Yes or no? Can I say that data set average will like come somewhere over here, right? So data set average you will be able to find out, right? Somewhere over here, somewhere in this particular place, you will be able to find out an average. So do we have an average? No, right? So average is equal to 0? No. Standard deviation is equal to 1? No. So in that case, what we will do? So I think we know the answer, right? Z statistics. So data minus mu divided by standard deviation. This is what we do, right? In case of a Z statistics, so data minus mu divided by standard deviation. This is what we try to do. And as a part of this standard deviation, we are trying to do what? Data minus average. We are trying to sift a data. We are trying to sift a data in such a way by subtracting a data set from its average. So in such a way that at the end of the day, your standard deviation is equals to 1 and your average is equal to 0, right? So fine, we can also shift this data. So we will try to create a new graph over here. So this is a step number 1. So it always, like I said, it always says that try to, right? So try to bring a data set to its standard normal distribution format. So this is a data set which I will end up creating, right? So which I will end up creating. Now this is completely fine. So from here to here, we are able to transform this kind of a data set because this is a basic nature of a principal component analysis. Principal component analysis never works on a normal distributed data set. It always works on a standard normal distributed data set. So make sure and keep these things in your mind that whenever you are trying to implement a principal component analysis, always go ahead with the standard normal distribution in a very first place, right? There is a mathematical proof as well that you will be able to find out, right? Okay. Now, once you will be able to do this, okay, once you will be able to do this, then what is our next step? So our next step is try to draw one single straight line which is going to, right, which is going to derive a data or which is going to explain a data. So I think we all know how to find out a best fitted line, right? This is what we have studied in case of our linear regression. So your residuals are supposed to be less as possible over here. So what you are supposed to do is, so I have a data, first of all, a raw data set I had. Now what I have done, first of all, I have converted my data set into standard normal distribution. so that I will be able to find out a better relations. My data set is not going to vary a lot, right? Now what I will do is just try to draw a straight line. And can I make it this statement that a straight line is a kind of a line, or this linear regression, the kind of a plot that we used to do, or maybe the kind of a line that we used to draw in case of a linear regression. So it's actually a kind of a line, right? Which determines or which derives the relationship of the data. Yeah. So which will be derived for both of this particular thing. So that is like a fine, right? So here we are trying to draw a straight line, a very simple straight line, which can derive the best possible or best fitted line we are trying to draw. So actually it's nothing new for us. So we are actually implementing a linear regression. That's it on in PCA, right? So we are trying to find out a best fitted line for a data set. So fine, this is a line that we all are able to find out. A best fitted line we are able to find out, right? So that so we always try to find out the best fitted line so that a residual will be minimum, right? Residuals are nothing but distance between line and the data set itself, square of the distances. So we try to basically draw the straight line. Now we all know that a straight line is nothing but it is trying to showcase a relationship. Simple, right? It is trying to showcase a relationship. So it is able to understand the pattern of the data set, right? Now, so we try to always draw this straight line, right? And like I said, so we always try to find out the best fitted line anyhow. And can I make this statement over here? Yeah, and again, so we can try to draw a multiple lines as well. There is no issue, right? Out of that, we can try to choose a best fitted line. Now, can I make this a statement over here stating that this line, a white straight line that we have drawn, it is a best possible relations that I can derive from the data set? It's a best possible relation, right? Because in linear regression, what we do? So can I say that we try to derive the best possible relations? Yes. Okay. Best possible relations. So best possible relation between what? Y and X, right? This is the meaning of the straight line. Ideally, this is the meaning of the straight line. So here I have again two axes. So let's suppose I have like a x1 and I have x2 over here. So we are just trying to find out a best possible relationship between this one. So this line is deriving a best possible relations in between two data set, at any point of a time. And let's suppose if I'm going to consider any point on this line, right? So if I'm going to consider any kind of a point on this particular line, right? Any point on this line. So can I say that any single point on this line contain both the coordinates x1 and x2? Yes or no? Because what is a formula? So here x2 is nothing but mx1 plus c. Can I say that in this case? Yes. So can I say that this is an equation of the straight line? So can I say that this any point on top of this straight line can be derived by this one? So it is actually containing a relationship between both of my axes. Yes or no? Yes. So basically this straight line is able to, this is what you are supposed to understand, right? This is the actual thing I'm just trying to explain to you, that here if I'm trying to plot even a single dot, that single dot is responsible for deriving a relationship between what? x1 and x2. Now, if you will just go back, what was the issue you were facing over here? So can I say that here issue was I was not able to represent all the coordinates in form of other coordinates. That was the issue that we were facing in this particular place, right? So we were not able to represent one of the coordinates in terms of other coordinates. But can I say that here we are able to find out something new. So where in by using one single coordinates, right? By using one single coordinates, one single lines over here, one single coordinates, one single dot over here, I'm able to represent both the components in the best possible way, that too. Yes. So this particular line, right? This particular straight line that we try to draw at any point of a time, right? This is called as principal component 1. So principal component line is nothing but it's a line which is holding a relationship of all the other components or all the components. So that is something called as principal component. So but here x2 before and after will be same after found from the linear equation. No, I'm just going to tell you like again a little bit extra over here that how it is going to change, right? Okay, so this is our best possible line that we are able to draw over here, and every dot is trying to represent a relationship in like of both x1 and x2. So just focus on this line part, right? Focus on the line part because this line is representing both the relations. Then what we can do is, so this is called as PC1, principal component 1, that we are trying to derive. Just try to rotate this line and make this line as an axis, one of the axis. So I'm just going to use a same line, right? I'm just going to use a same line over here. So this line I'm going to use. So this is a line that we have over here. So I've just rotated this line, PC1, right? So this is a PC1 that we have, and PC1 is able to derive what? So PC1 is able to derive almost all the data points. So once I will just try to rotate. So I have 1 point over here. I have another points over here. I have 1 points here. I have another points here. Then this is one of the points. Then this is the another point. Then this is the another point. This is another point. This is another point that we have. So fine, we are able to draw this PC1, and I've just like rotated this line, right? Just one single rotations I have done so that my x-axis will be this particular line itself. So I'm just rotating all the data set along with this one, right? As you can see, so I'm just like trying to rotate these entire things. Now here, so if I'm going to draw, right, if I'm going to draw a perpendicular line over here, because see, so we are able to find out a line which is trying to derive a relationship between x1 and x2. That's completely fine. This is a line which is deriving, which is responsible for deriving a relationship between x1 and x2, right? But at the same point of a time, right? So this component we can represent on this one, on this one, on this one, on this one, this one, this one, this one, this one. So we can try to represent all of these components on top of this particular line. So this points, these are the points which is going to give you a principal component 1. These are the points which is going to give you a principal component 1, or one of the axis which is going to give it to you. And yes, so now if you have to form a new coordinate system, right? If you have to form a new coordinate system, so how you will be able to form? So a new column is nothing but, so if I'll ask you, just can you please give me a new column? So this one is, let's suppose, a value 1, this one is value 2, this one I'm talking about, this one is value 3, this one is value 4, this one is value 5, this one is value 6, this one is value 7, this one is value 8, this one is value 9, right? So V1, V2, V3, V4, V5, V6, and so on is representing a new column, which is a combination of what? Which is a combination of X1 as well as X2 column, or which has been created as a part of contribution of X1 as well as a X2 column. But at the same point of a time, there are certain things, or there are certain points that we have missed out. And what are those points? So when we are trying to represent one of these coordinates on top of this straight line, so yes, this was having this component, but apart from that, this is having even this components, right? It is having even these components. So we are supposed to consider other components as well. So this is something called as PC1 that we are able to create. A PC1 is nothing but it's coming from the straight line. But there is a chances that I have missed out some of the information. I'm able to represent my all of these information with respect to a straight line as a relations, right? I'm able to represent all of these things as a part of this relations. But there are some points, there are some chunks which I'm not able to represent maybe, right? So if I'm not able to represent those things, right? If I'm not able to represent those things, so what I will do is, so I will try to create a new axis. So for sure, if we are trying to create a new axis, so we are supposed to draw a perpendicular line, because for sure degree between two axes must be 90 degree, right? So we are going to draw one perpendicular line on top of it, and we are calling this one as a principal component 2. So principal component 2 is nothing but a perpendicular line on a principal component 1. And principal component 1 is nothing but it's a straight line which is showing a relationship. That's it. This is something called as principal component 1, principal component 2. Principal component 3 is nothing but, if let's suppose I am trying to reduce 100 dimension data into 3 dimension, right? So principal component 3 is nothing but, right? So principal component 3 is nothing but it's just a component perpendicular to principal component 1 and principal component 2, or you can say it's a z axis. So this intuition is fine. We are like able to understand something, we are able to understand something not, that's completely fine. But the problem over here is that let's suppose I have 100 number of, right, columns, 100 number of columns. Now in how many columns I'm supposed to reduce it, whether it is supposed to be 2, 3, 4, 8, 10 or 20. Means when I'm saying 2, I'm trying to say that we'll try to find out two principal components, 1 and 2. When I'm saying 3 columns, so 100 column we are converting into 3 column. So it simply means that I'm trying to represent like 100 columns into principal component 1, 2 and 3. I told you in a very beginning, it's not an elimination, it's a reduction. So reduction means we are completely trying to transform a data set in such a way that we will be able to hold a relationship on nature of the data, but value wise, we are trying to change. This is what we have done over here. A new value we are trying to generate. Principal component here, so 4 number of columns simply means that we are trying to generate a 4 principal component here, 8 principal component, 10 principal component, 20 principal component. So this is the meaning of it, right? But the question arises over here that how many principal component I'm supposed to derive, right? And every time principal component line becomes x, become the x-axis, is it? Yes, of PC1. This is PC1, principal component 1. Principal component 1 is one of the most contributing component. Principal component 2 will be having a less contribution. Principal component 3 will be having a less contribution. Why? What is the reason? Because PC1 is a kind of a line, kind of a straight line, right? Which has been drawn based out of your relations, right? And rest of the principal component is just a perpendicular on top of the first one, right? So this PC2 will always pass through the mean point of the PC1, so that, see, we are just trying to like rotate it, right? So this mean point is nowhere going to change. Simple, right? So if you are going to draw a PC2, so for sure it will be a perpendicular and at the same point of a time. It will be just a perpendicular. You can just assume in this particular way. Okay. Now here, right? My question is that I have 100 number of columns, right? Now someone is telling me that, okay, I'm trying to build a model, but it is not giving me accuracy. So I have suggested them that, okay, just do one thing, try to use some dimensionality reduction technique. Now a person is asking me that, okay, I can use a dimensionality reduction technique, but in how many columns I'm supposed to decompose? 2, 4, 5, 8, 10, 90, because I have 100 number of total columns, right? So how I will be able to get that particular answer? So we will try to find out. But before moving ahead, are you able to understand a little bit of this one? What we are trying to do over here? How we are trying to transform a data set with the help of this straight line? Yes, a little bit at least, right? As of for now, because there are so many things we are yet to discuss. So as of now, I'm just expecting a little bit of understanding. PC2 and PC3 is not clear. PC2 is nothing but just a perpendicular line on PC1, right? So see, if I have a data set, let's suppose if I'm like trying to explain in this way. So let's suppose if I have a data set. So can I say that I have to like this data set can be explained with respect to this as well as with respect to this? If I'm explaining just with respect to this one, so maybe it's not a clear explanation, a partial one, right? So this is maybe a PC1 and this is a PC2. So PC2 is nothing but perpendicular line that we used to draw. So another axis. So we are actually trying to do only one thing over here. We are actually trying to change the original axis itself. If you observe, right, are we using the original x1 and x2 axis? Original axis was what? Can I say that original axis was x1 and x2? Yes, original axis was x1 and x2, right? What was the original axis? Or original axis means original column name. So can I say that my original axis was x1 and x2? Yeah. And we have, can I say that we have just changed the entire axis itself? So now we have derived the new axis, PC1 and PC2. So we are actually changing the axis of the entire data set itself. So for sure, we have to represent it with respect to other axis as well. Fine. Now here, my question is that how many principal component we are supposed to derive? So 2, 3, 4, 8, 10, 20. So that answer I will be able to find out from something called as EVR. Okay, so that answer I will be able to find out from EVR. Explained variance ratio. Now, what is a meaning of explained variance ratio, right? So can I say that when we are trying to create a principal component 1 and when we have data points in this way, right? When we have a data point in this way, so some of the relationship I can try to derive with respect to a PC1 and some of the relationship I have to derive with respect to a PC2. Can I say that? Yes, because if this is the point, so for sure I can try to represent this points with respect to PC1 and a PC2, right? So my question is, let's suppose I have a third coordinate as well, a PC3, right? I have a PC3 over here, a principal component 3, a third axis I'm trying to recreate from my side, right? So how I will get to know that whether I'm supposed to create this 3 axis or I'm not supposed to create a 3 axes? Maybe I should start with the one single axis. So here is a things, right? So EVR, we try to find out for each and every principal component. So explained variance ratio, it simply means that one principal component, right? One principal component, what is a capacity or what is what is a probability, what is the capacity that this one single line, or how much relations this one single line is able to explain. That is something called as explained variance ratio. Let me simplify these things for you, right? Let me ask you a question over here. Let's suppose there is a data set, right? There is a data set which is available in this particular place. I'm trying to draw the straight line, right? Now I'm saying that accuracy of this straight line is 83%. What is the meaning of it? I have the data set, I have drawn the straight line, I'm saying that accuracy is 83%. What is the meaning of it? Yes. What is the meaning of this one? So can I say that the meaning of this 83% is that this line, this straight line is able to explain 83% of the data? Yes. This line is able to, this is something that we can derive from our R square, adjusted R square value from our linear regression classes. Yes. So this is the actual meaning that, okay, fine. So it is able to derive, or it is able to showcase 83%, right? It is able to explain 83% of the data. Now, what about 17%? What about rest of the 17%? So maybe if I can draw some other line, so maybe that line will maybe that will be able to explain, right? So similar things we are trying to perform over here, right? So maybe one particular line, if I can draw on top of this line, so maybe this line will be able to explain rest of the things, because at any point of a time, this is the dot, right? And this is the dot for this line. So for sure, it will be having x component, and it will be having this axis component, this axis components, right? So explained variance ratio says a same thing, that it's completely fine. You have drawn the principal component, PC1, PC2, PC3, PC4, PC5. There is no issue, right? But I will tell you that what is a relations, that what is your capability to derive a relations. So that is something called as EVR, explained variance ratio, in this particular place. So EVR, explained variance ratio, for PC1 we can try to find out, and this is nothing but again a same thing that we already, like, I think we all are aware about it. Distance of PC1 points divided by PC1, PC2. So let's suppose we have two like a PCs. If we have three PCs, then distance of PC1 divided by distance of PC1 to 3. If we have 4, then distance of PC1 divided by 1, 2, 3, 4, right? So all those things. This is something called explained variance ratio. So distance of PC1 points, right? So here, what we try to calculate. So we try to calculate, this is a PC1, let's suppose, right? So this is a distance, this is a distance, this is a distance, this is a distance, this distance, this distance, this distance we try to calculate. This is called as distance of PC1 points, because these are the PC1 points, divided by distance of PC1 points and this distance. This is from PC2. So what is the distance between PC2 and this two line? This one, then this one, then this one, then this one. We try to calculate. So distance of a PC2. And this is going to give you what? Explained variance ratio. So let's suppose, right? Let's suppose distance of a PC1, right? Distance of PC1 point. So if I'll try to do a distance summation of this one, this one, this one, this one, this one, this one. So let's suppose it is going to be a 50 divided by this distance, means 50, plus let's suppose this, the summation of this distance is equal to 5. So 50 by 55 is equal to 0.91, right? So what is a meaning of EVR for PC1, PC1 0.91? What is the meaning of it? Yes. So can I say that basically this PC1 line that I'm able to draw, it is able to retain a 91% meaning of the data, right? So can I say that? Fine. Okay, some people are like getting confused with respect to distance part, right? So let me like clarify these things. See, these are the points, right? Simple points I will try to take, only these many points. Let's suppose this is PC1, this is PC2. I think we are clear, right? How we are deriving a PC1 and PC2, how we are able to get a PC1, PC2. Till this point, it's clear? Yes? Okay. Now we are trying to find out. We have drawn PC1, PC2. We don't have any issue, right? But we have to check even a capability, because it's at the end of the day, it's basically a relative result that we are trying to find out, right? We are not trying to change a meaning of the data. That's the reason. So we have to consider the factors with respect to all the coordinates, which is available one. Let's suppose if I have 100 dimensions. So with all the 100 coordinates, 100 dimensions, we are supposed to find out. So here, distance of PC1. So can I say that this distance, this distance, this distance, this distance, and this distance, right, is nothing but distance of PC1 data and PC1 line. This is the distances, this is the distances, this is the distance, this is the distances. Agree, those who are having a problem with the distance part for PC1, right? Okay. Now distance of PC2. Can I say that this line is PC2, right? This line is representing PC2. So which distance? This distance, this distance, this distance, this distance, and this distance. So can I say that all this white line is representing a distance of PC2 and red line is representing distance of PC1, right? So we are just trying to find out that, okay, how far it is, right? How far my principal component 1 is. So can I say that we do a same thing in case of R square? Almost, right? We try to perform residual summation of a square. Residual summation of a square is nothing but distance between my data set and a line, perpendicular distances between a data set and the line. I think this is what we do, right? In case of a residual summation of a square. Although residual summation of a square is 1 minus RSS divided by TSS, total summation of a square, where total is nothing but just to like give you a value in between 0 to 1, right? TSS that we try to calculate in general. So here, PC1, 0.91. A simple meaning is, so my principal component 1, a line that we have drawn, is able to explain a 91% of the data, right? It is able to explain a 91% of the data set for me at any point of a time. Now, similarly, if I will try to calculate explained variance ratio of a PC2. Now, what is the explained variance ratio of PC2? Can I say that 5 by 50 plus 5 is equal to what? Is equal to 0.09? Yes, so is equal to 0.09 over here. So can I say that 0.91 and 0.09, right? If you will combine, it's going to be 100%. Yes. So can I say, can I make a statement over here that I'm not trying to change a meaning of the data set in actual? What I'm trying to change over here is an axis, right? An axis by which I will be able to derive a data set, because, right? Because the problem is, right? So let's suppose if I'm going to take a data set in its original format, if I'm going to consider a particular data set, right, in an original format. Now, so let's suppose this is my line and this is my data set. Now, can I treat this x-axis as a straight line itself, x1 as a straight line itself, right? And can I say that it is possible to even find out that what is a ratio this line is going to explain? Just think in this way, right? Just try to visualize. So can I say that even this x-axis, original x-axis as a straight line, I can try to consider for this data set, and even I will be able to find out a EVR, explained variance ratio, or even residual? Is it making sense to all of you? So I'm just telling you that just take a data, right? This is my data, right? Now you draw a straight line. Just don't draw it. Just use a same x1 and x2, right? Now x1 is my straight line and x2 is my straight line, let's suppose that I have. Okay, so x1 is a straight line and x2 is the straight line that I have over here. Can I say that even I can treat x1 as a linear model, right, for this data set, and I will be able to find out a ratio, or I will be able to find out a R square, that how much how much variance this line is able to explain it to me? Is possible, right? Yes or no? Yeah, so residual will be very, very large for sure. So we are aware about it. Residual will be very, very large. So in that case, R square will be very, very less. Can I say that? Can I say that? Yes, it will be a worst line. I agree with it, right? But what I'm trying to say over here is, so is it possible to derive a relationship with respect to this line? Possible, right? So let's suppose residual or R square is giving you maybe a 20%. So can I say that this line is able to explain only 20%? And maybe for this line, it is going to give you 80%. So can I say that both combinedly, both of this line, both of this x1 and x2 coordinates is trying to explain all the data set? So if I have to explain this data set, what I will do? Can I say that I will be using x1 component and x2 component? If I'll ask you, right, derive one particular points in a space, how you are going to derive one particular point in a space with respect to x, y, and z coordinates? You will be able to derive. Otherwise, there is no other values by which you will be able to derive it. Agree, everyone? Right? So when data was available in its original form, even at that point of a time, right, it was possible to derive a data set with respect to any of these axes, right? But what we have done over here, as a part of principal component, we have chosen a line, right, which will be able to derive more. Can I say that this is the only thing that we have done in principal component? Yes, this is the only thing that we are trying to do, right? And here, so yes, we are trying to create a PC1 and PC2. So how many PCs are possible? What is the maximum number of PCs which is possible? Right? So maximum number of PCs are nothing but total number of the columns. Let's suppose I have n number of columns. So n number of PCs I will be able, in general n minus 1. Yeah. So n number of PCs I will be able to generate. And then n minus 1 generally we use to select at least. Otherwise, there is no meaning of generating n number of PCs. Then I will not be able to do a dimensionality reduction, right? I can generate n number of PCs. That's true, right? But the problem is like if I have 100 column and 100 PCs I have generated, then what is the meaning of dimensionality reduction? At least n minus 1 I'm supposed to consider, right? So okay, so here the thing is that this PC that we are trying to create, so this PC is nothing but it is trying to derive the complete variance in between the data set. So what we do is, so here we try to plot one graph called as screen plot. The screen plot we try to draw. So where on our one of the axis we try to keep dimension, and here we try to keep EVR, explained variance ratio, right? So here, if I will try to increase a dimension, PC1, PC2, PC3, PC3, PC4, so total explained variance ratio will keep on increasing, and after a certain point of the time, it will be stagnant, right? So explained variance ratio will always be in between 0 to 1, right? So here, let's suppose I have a dimension 1, then 2, then 3, then 4, then 5, then 6, then so on, and then 100. So let's suppose I had 100 column, right? But if by using just a 4 component, 4 dimensions, if I'm able to explain a 90% of the data, if by calculating this EVR, explained variance ratio, right? If I get to know that, okay, if I'm using only 4 component combinedly, right? Let's suppose here only one component itself is able to explain 91% of the data set. It's completely fine. Why to take the other one? Remove it, right? 90% meaning of the data set is more than enough. 90% variance of the data set is more than enough over here. So I'm not supposed to consider maybe the another one or maybe the second one. So here what screen plot will give you is, again, it's not giving you something new. It's the same thing. If we are, it is going to tell you. So if you are able to find out that only 4 dimensions, means 4 PCs are going to explain a 90% variance of your data. So can I say that it's better to take only 4 PC or 4 new derived column instead of taking 100 number of columns? Yes, instead of taking 100 number of columns, it's better to take only 4 columns, because what is a problem I have listed down in the beginning? Time complexity. So I will be able to reduce, if out of 100, if I'm selecting not out of 100, out of 100, if we are able to derive only 4, which is explaining a 90% meaning of the data set, right? In terms of generalizing a relationship, yes, it will be easy, right? So at the time of maybe finding out the save of the data set, yes, it will be easy for me, right? So all of your features will be contributing, because you know about it. These 4 features are contributing 90% plus individual EVR. You will be able to calculate explained variance ratio. So which feature is contributing by what value, even you will be able to find out these things, right? So something like a elbow plot, it's not like a elbow plot, yeah, but you can relate, but it's a screen plot, we used to say, right? So just a dimensionality versus EVR. So this is something that you will be able to find out. So with the help of screen plot, so you will be able to see that, okay, what is basically a relationship is, or how many principal components are required to actually derive a particular data set, right? So this is something that we can try to do. So principal component, mathematically, it's nothing but, so it's a straight line and then rotations of the straight line, and then we are trying to uh, just represent a data set with respect to a different coordinates or different axes. This is something that we are theoretically, this is something that you are supposed to understand. Now someone is asking me that what is eigenvector here? Eigenvector come in another places. There is a multiple way to do a principal component analysis or dimensionality reduction. Eigenvalue and eigenvector is one of the mathematical way of doing it. Even eigenvector and eigenvalue does the same thing, which I'm going to explain you. Well, I'm going to explain you my examples. How can we decide how many PCs can be created based on the EVR and dimensionality? So this is the screen plot. So let's suppose if 4 dimension itself is going to explain 90% of the result. So in that case, I'll be taking like a 4 dimension instead of taking a 100 dimensions. Yeah, so if in this way, if you are going to explain, I think you will be able to understand in a better way. If you will start with the eigenvalue, eigenvector, you will be lost, believe me. And once you are able to understand this one, then I will explain you eigenvector and eigenvalue, and then you will say, I think we are talking about the same thing. So, okay. So now, let's take a break of maybe 15-20 minutes, right? We'll come after the break, and then we will try to take some data set, and with that, we will try to prove it, right? Whatever theoretically we have discussed. So with respect to a data set, we'll try to prove each and everything. So let's take a break of 20 minutes. So now it's 4:52. So maybe by 5:12, we'll be on break. After 5:12, so we are going to resume, and yeah, just go and freshen up yourself. Fine. Practicals after break. Yes, practicals after break. Okay, so fine, everyone. I think we are back, right? Can you guys confirm we are back? Okay, fine. Today, India versus Pak match. I don't watch cricket, so I never watched cricket in my entire life, so I don't even know whether there is a match or not. Okay, World Cup. No, I don't even know cricket. The major problem with me is like I don't know cricket, so it's like whether it's a World Cup or it's like something else. So it's like equal for me. Yeah, I know like many of you are not many, almost all. India is a cricket loving country, but still. Okay, so fine. Let's try to like do it. This is not a match. This is a war between India and Pakistan. Okay, fine. Dipendra, yeah. State number 4, state number 5. This is good. You are outlier. Yes, yeah, I am. That is like a true. Dipendra. Okay, so Dipendra, just do one thing. Just ping me like entire things at a time. I'll just post it in a like with everyone. You are not a part of mainstream Indian population. I also don't. Yeah, David. So we are together in that case. Okay, so let's try to understand. Forget about match, right? This is important. So people are not going to ask you like about a cricket match in your interview and in your job preparation, but yeah, so they may ask you a couple of questions from here, and you will have to explain. Not a match. This one. Fine. So just try to do one thing. So import NumPy. Open up your notebook, guys. So sooner we will be able to finish it. You will be able to get a time to go and watch a match. So NumPy as NP, right? And maybe we can try to create a simple data set over here. So NumPy array we can try to create in this particular place, right? Of maybe a certain shape, right? So maybe I can try to create certain sort of a data set over here, right? Uh, where we have like multiple rows and two columns. Let's suppose x1 and x2 kind of a columns. If we can try to create, yeah. So let's try to like do it. So here I can try to use maybe this as an array. So this is a data set which I'm able to create, and this is how my data set looks like, right? So this is a data set, right? And as you can see, you can even use a data frame. There is no issue because in a later stage we are anyhow going to use like a data frame. So we have two columns, x1 column and we have a x2 column, right? So we have two columns over here, x1 and x2, and what we are supposed to do is, so we are supposed to apply a dimensionality reduction technique on top of this one by using a raw calculation, not by using a PCA equation, because you will call a PCA equation and just within one single line, you will be able to decompose it. But we are not expecting that, right? So we are supposed to prove all the theoretical concepts as well. And that is the reason. So we are not going to perform our same operations like just by using a PCA. That we will do in a very last stage. Then when we will be able to prove each and everything, then maybe we can try to do it. So maybe if I can try to show you a shape, right? So what is a shape of it? So shape of this one is 6 rows and two columns. This is the shape of this particular data set. You will be able to find out. Now let's suppose if I'm trying to find out mean, because in a very beginning I told you that your data set is supposed to showcase, right, stand, or if your data set is not available in a form of standard normal distribution, then in that case you will have to convert your data set in a standard normal distribution format. You can directly call a standard scalar, pass your data set, and it will be able to convert. That is completely fine. Let's try to check whether this data set is available in a standard normal distribution format or not. right? So maybe I can try to print axis mean, right? So maybe mean across different like rows we can try to consider, so that all these rows values it will be able to take, or even just by using a calculator, or even without using a calculator, I believe you all will be able to calculate a same thing. So 3 plus 7 plus 1 plus minus 4 plus minus 4 plus minus 3, right? So what will be the value? Can I say it is going to be 0? Yes. So can I say that it is going to be 0? Let me ping you this one, guys. Yeah. So can I say that we have already taken a data set which is available into a standard normal distribution format. Mean is equal to 0. Standard deviation, if you are going to calculate, so standard deviation is equals to 1. Next data set that we are going to consider, right, a big one. So over there we can try to call a standard scalar, so we are not supposed to perform any other kind of operations in that case. Let's do one thing. So maybe just try to convert this data set into a data frame format, right? So here we can try to call import, maybe import pandas as a PD in this particular place, and we can try to convert this numpy array into a data frame. So pandas dot, maybe we can try to call a data frame. So vice versa is possible. We can try to pass this one. So now it's converted into a data frame format, right? So I have created one very simple data set, and I'm trying to convert these things into a data frame. Let's suppose I would like to give a column name. So let's suppose A0, and A1 is a column name that I would like to give over here. So A1 is a column name. So this is the column name which I have already given, A0 and A1. So that's completely fine. So we have not done anything else with the data set except converting this entire data set into a data frame. And this is my data frame that I'm able to see. So again, in this data frame, we have two columns, same, and A0 and A1. If you will try to consider, or if you will try to find out a mean of this A0 column, it is going to be 0. The standard deviations, if you are going to calculate, so it is going to be 1. If you are talking about A1, so again, mean of A1 is equal to 0, and standard deviation of A1 is equals to 1. Okay, fine. Now, what maybe we can try to do is, so we can try to perform this some of the operations on top of these data set. Or when I say a data set, so maybe on A0 and on A1 column, so we can try to perform some sort of a operation. Now, what kind of operations we can try to perform over here? Let's try to understand that in a very first place, right? So here we are going to establish a relationship between A0 and A1, that how correlated this A0 and A1 is. And this relation will be shown by always a factor called as covariance, right? So covariance always try to find out, or it always try to measures that how one variable is changing with other variable. So let's suppose how 3 is changing, or how 3 is related to a 7, how -4 is related to a 6, or how this A0 column is related to a A1. So this is something that you will be able to find out of covariance. I'll just show you a very simple example right over here. So let's suppose I have this kind of a data set. So can I say that this data set is showing me a positive covariance, right? If one data is increasing, if one axis value is increasing, other value axis value is also increasing, right? So it's a positive covariance it is going to showcase, right? Again, so if I'll talk about maybe like this kind of a data set, right? Can I show that it is showing me a negative, one is decreasing, other is also decreasing? It's kind of a negative covariances it is trying to showcase. Now, if I'll try to show you this kind of a data set, so what is a covariance which is available over here? Can I say that there is no covariances I'm able to find out? Means there is no relationship which I'm able to find out over here. So kind of a zero covariances we are able to find out. Yes, we have studied covariance during the statistics class. Yeah. So I'm just talking about a same kind of a covariances. Now, can I say that when we calculate y is equal to mx plus c, so m plays a similar kind of a role? Yes. So it always try to tell you that how y is related to a x values, right? So I think we were talking about a straight line when we were trying to find out a principal components, right? So fine, if I will try to find out a covariances, I will get to know that how one is related to a others, right? So I will be able to find out these particular factors. So we have to find out first of all a covariances between these two columns mathematically, so that I will be able to find out a relations that okay fine. So what is the relationship between one and another data set at any point of a time? So if we have to find out a covariances, so covariance formula says that, so formula wise, if manual calculation, if you have to do, so covariance always says that, let's suppose we have a column 1 and column 2. So covariance between two columns, if we are trying to find out, so it always says, right? It always says that covariance is nothing but a column data. So let's suppose C1 column data minus average of C1 into C2 data minus average of C2, right? Divided by total data minus 1, summation of this entire things is going to give you covariances, right? So this is something that you will be able to find out as a covariance. Covariance is nothing but, so let's suppose if I'm trying to find out a covariances, so how I will be able to find out a covariances? So can I say that we have this column and we have this column? Now what is the average of this column? 0. What is the average of this column is equal to 0, right? So covariance of, if I'll have to find out A0 and A1, so what will be the covariance? So 3 minus 0, right? 3 minus 0 into 7 minus 0 divided by what is the total number of records? So total number of record is equals to 6. So it is going to be 5 over here, plus minus 4 minus 0 into minus 6 minus 0 divided by 5, plus we can try to say, so again, like we can try to take a common as a 5, that is also fine, because anyhow in a denominator calculation it is going to be a 5 itself. Then 7 minus 0 into 8 minus 0 divided by 5, plus 1 minus 0 into minus 1 minus 0 divided by 5, plus minus 4 minus 0 divided by 5, plus minus 1 minus 0 divided by 5, plus minus 3 minus 0 minus 7 minus 0 divided by 5. So can I say that if I'll try to calculate this one, I will be able to find out a covariances, right? So what is a covariance between column A0 and column A1, right? So I think number of the data values are 6. So it's a m minus 1 that we have written, right? So number of data set minus 1. So it's actually going to be 5. Okay, fine. So this is something that we are supposed to write down. So why is m minus 1 and not m? So, okay, there is something called as Bessel correction, right? So that is a concept which is applicable even over here with the sample data set with the population. So we can try to take even m, that is fine. So can I say that I will be able to find out the covariance? So if you will do the calculation, you will be able to find out 25 over here as a covariances. This is something that you will be able to find out at any point of a time as a covariances. So I believe this is completely fine. We are able to so this is something that we are able to find out in the easiest possible way. So fine, we are able to find out that covariance between column A0 and column A1 is equals to 25. Fine, programmatically we can try to calculate a same thing, right? So if I have to calculate these things with the help of maybe a programming, so I have to extract maybe a A0 column. So what is my A0 column? A0 column. So A0 is nothing but, so I had a numpy variable, right? And that variable was basically A. So A0 is nothing but A of my array of all the rows and only 0th column. And then I can try to write A1 is nothing but A of all the row first column, right? So find A0. I will be able to get, and A1 I will be able to get. A1 I will be able to get. Now, if we have to find out like covariances in this particular place, right? So what we can try to like do? So maybe we can try to write down in this particular way, right? So again, 3 minus 7, sorry, 3 minus 0. So 3 into 7, 4 into minus 6, 7 into 8, 1 into minus 1, minus 4 into minus 1, minus 3 into minus 7 divided by 5. So can I write it down in that way? Yes. So can I write these things, entire things in this way? Yes. So that I will be, since mean is equal to 0, right? So it's completely fine. We are not supposed to like write all those like things. Or else what we can do is maybe I can try to call numpy dot covariances, and then I can try to pass these two columns A0 comma A1. I can try to pass. So here we are able to get a matrices, right? So this diagonal one is representing basically a covariances. So here you will be able to find out this is A0, A1. This is A0, this is A1, right? So what is covariances between A0 and A1? 25, A0, A1, 25. So this is something it is trying to represent. What is a covariance between A0 and A0 itself? You can try to even calculate that one, because both are just a data set, right? So covariance between A0 and A0. So this is something that you will be able to find out separately, and A1 and A1. So this is something that you will be able to find out. But this is representing a covariances in between. So this diagonal is representing your covariances A0 and A1, right? So it's been represented by diagonal element for sure. So numpy dot covariances, we can try to find out. We can try to find out even in other way. So it's completely like a fine. It's not like I will not be able to find out just by writing manual calculation. So even I can do a manual calculation and I will be able to find out the same thing. Let me do that. So numpy dot summation of what? Summation of, maybe I can say summation of A0 into A1. So summation of A0 into A1 divided by, so divided by maybe a 5. So it is going to be a 25. So even in this way, I'm able to find out the same values, 25. So again, I'm aware about a fact that it is mean is equal to 0. So I'm able to find out a covariance in this particular place. So this is completely fine. We are able to find out a covariances. It simply means that we are able to find out the relationship in between, right? Relationship in between we are able to find out. There are other way as well by which I will be able to find out a covariances. So two ways I have explained you. One by writing a manual calculation, one by using a numpy dot covariances, and then maybe a third way is transpose of matrices into the matrices divided by m minus 1. So even this is going to give you a covariances itself, right? So transpose of the matrices. So let's suppose if I have a matrix, right? So just try to transpose it and then multiply this matrices by a matrix itself divided by total number of component minus 1, total number of like attributes minus 1. So even this is going to give you matrix multiplication of, again, matrix multiplication, not a normal multiplication. So even this is going to give you this one. So why NP dot covariance is giving 2 into 2? Because what it does is, so it will try to create this matrices A0, A1 and A0, A1. So it will try to fill all the values. So covariance between A0, 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 A1, A1, A0, A0. So this is just a nature of the output that it try to calculate, right? So in a denominator, it's the same thing, m minus 1. Okay, if it's not visible, so it's m minus 1, means total data minus 1 for the sample data set. So we can even try to calculate our covariances by using this one, and we will be able to get a same result. So I'm just showing you a three ways by which you will be able to calculate it. So let's suppose this is my matrices. So what will be a transpose of this matrix? Just rotate it. So this is the transpose of the matrices. What will be a matrix multiplication? So A dot transpose matrix multiplication wise, I'm supposed to use @ symbol. I think we have already discussed about these things in our NumPy classes. So this is the values. Now, if we are going to divide these things by m-1, what is m-1? So basically it's a 5. So can I say that we are able to get the same thing? So NumPy dot covariance is doing a same thing internally. Is it fine? Yes. So three ways by which I will be able to find out the covariances. One, by directly using a formula, data minus its mean. So one column data minus its mean into another column minus its mean divided by m-1, summation of the whole data set. So in this three way, I will be able to find out covariances. That is fine. We are able to find out the covariances, but what is the use of it, right? Why we are trying to find out these covariances and what is a use of it? I think we are supposed to understand that in a very first place. So let's try to understand a concept of eigenvalue decomposition, right? And where this eigenvalue decomposition comes into a picture, what is our relations and how it is going to help you out in terms of finding out your principal components, right? So just keep all those things in a mind that we have discussed theoretically so that you will be able to relate this one, right? Okay. So here, covariance we are able to find out, but eigenvalue, there is a concept called as eigenvalue and there is something called as eigenvector. You will be able to find out. Now, what is the meaning of this eigenvalue and an eigenvector? In general, you will be able to understand. So, eigenvalue, mathematically, if you will try to understand, right? So, eigenvalues or eigenvector is nothing but, so eigenvalue or definition says that so whenever you are trying to find out or there is a possibility to showcase any of the data by using some of the constants or by multiplying. Let's suppose I have x1 and x2, right? So here 2 4 3 8 is given to you, then 4 8 6 and 16 is given to you. Now if I'll ask you, I'm not looking for x2 column, so can you please try to represent x2 column as a x1 column, right? Can you please try to represent x2 column as a x1 column? Fine. So what you can do over here? So yes, you will be able to represent. So x1 is equal to 2, 4, 3, and 8. So x2 is nothing but 2 into x1. So 2 into 4, 2, sorry, 2 into 2, 2 into 4, 2 into 3, 2 into 8. So can I say that you are able to represent even x2 in a form of x1, right? Now what you have done over here, so can I say that you have multiplied the entire data of x1 by some constant in this particular place to represent x2 as a x1? Agree, everyone? Yes. So can I say that I'm able to represent x2 as an x1? I don't need x2 now, right? I don't require x2 because I'm able to represent it. Similarly, eigenvector and eigenvalue says that yes, it is possible to represent any vector, right? Any vector in any other vector format or which is a derived vector format of the existing vector if you are able to find out this constant, right? If you are able to find out this constant. So this v will become nothing but it's an eigenvector. When I'm saying eigenvector, so I'm not talking about any fancy terms over here. I'm just talking about your row columns in this particular place. In a layman way, if you will try to understand. So I'm just talking about your columns, right? And lambda is nothing. So v is called as eigenvector. So there is a possibility to represent any vector. And what is called as vector? Anyone? What is vector, by the way? So any points which is having a magnitude as well as a direction, right? Means a value as well as a direction. So that is something called as a vector. So in any like a n dimension, so if we are trying to represent a data set, so yes, it can be treated as a vector, magnitude plus direction. So fine, our data set is there. This is a vector and we are supposed to find out this one. So if we are supposed to find out this eigenvalue and this eigenvector, right? This eigenvector and this is called as eigenvector and this is eigen equation, right? So real eigen equations you will be able to find out. So if somehow I'm able to find out eigenvalue and eigenvector, right, my work will be done and I will be able to perform. Okay, so here what I was saying is like if we are able to represent, right? So if we are able to represent some of the values in some other format, in some other vector format, so it's like a possible, or it's possible for any one of us to, and it is possible actually, it is possible to represent either of these two columns maybe into some other format or in some other form. And yes, that can be like a, we can try to achieve with the help of eigenvalue or maybe a eigenvector. So let's try to understand this particular part. So what is a meaning of this eigenvalue and a eigenvector? So let me try to store this result, right? So maybe as a sigma, we can try to store this particular result, right? So that I will be having a covariance of this two data set, right? Now, what is the next step that we can try to do? So we can try to find out that what is our eigenvalue and eigenvector of this relations that we can try to draw. So covariance matrices we are able to get, right? Means relationship between two data points we are able to get. Relationship between one column and the other columns we are able to get. Now what we can do is we can try to call numpy dot lineage dot eigen, right? And then we can try to pass basically a sigma over here, sigma. So it is going to give me these two data sets. Now let's try to understand what is the meaning of this eigen. So it computes the eigenvalue and right eigenvector of the square array. So any square array or any covariance matrices, if you are going to give, and covariance matrix is what? It is representing a relationship between A0 and A1. This is what it is trying to do, right? It is just trying to represent a relationship between A0 and A1 at this point of a time. So here, right? So when it is trying to represent a relationship between A0 and A1 in this particular place, right? So we are trying to like out of that, we are trying to compute what is a value of eigenvalues and what is a value of eigenvector over here. So ideally, we are trying to calculate. So let's suppose this is a transformed data. So we are trying to calculate lambda and v. So we are trying to calculate that, okay, fine. So what kind of a vector we can take, and what kind of vector means a column or data we can try to take, and with what value I'm going to multiply so that I will be able to achieve a data set, or I will be able to achieve the original data set. This is what it is going to represent. Now here, right here, when we were talking about a theory, so we have discussed about this one. We discussed that we are going to draw a straight line, right? We are going to draw a straight line. So can I say that component of this point on a straight line will be this one, and it is having some directions as well as it is having some magnitude component of this one on this line, and then we were trying to find out component of same data on the other line, other principal component, right? So whenever you are going to talk about this eigenvalues, so eigenvalues always tells you that, okay, what will be a one component and what will be the other component. But how you will be able to define that which one is PC1 and which one is PC2? So whatever eigenvalue will be the highest one, whatever eigenvalue will be the highest one. So this is representing, this two array is representing eigenvalues, because we are supposed to calculate PC1, we are supposed to calculate a PC2 out of this one, and this is the vector that we are able to draw. This is the vector that we are able to find out based out of the covariances. Means line is representing the relation and covariance was representing the relations. So based out of that, so we are able to find out the covariances, and now it is giving me value of a lambda over here. So what is the value of lambda? So value of lambda is 56.92 and value of lambda is 3.07. So why two value of lambda we are able to get? Because we have two principal component and at max we have two lines or maybe two columns that we have. If we have three columns, three eigenvalues I will be able to get. If we have four columns, four eigenvalues I will be able to get. If we have five columns, five eigenvalues I will be able to get. So if I have n number of columns, n number of eigenvalues, I will be able to see over here. That is completely fine. So here, if I have to calculate a PC1, because my responsibility is to calculate a PC1 and my responsibility is to calculate a PC2, because I'm trying to transform A0 and A1. So out of covariance, lambda I'm able to calculate, right? And its respective vectors I'm able to calculate over here. So now let's just try to do one thing. So we'll try to separate this data. So maybe there are two outcomes inside a tuples. So I can try to store this as L and X, right? So where L is nothing but it's representing your eigenvalues. So these are the eigenvalues, and your X is nothing but it's representing a eigenvector, respective eigenvector for the respective eigenvalues. And it is true that we can try to represent any data as a part of eigenvalues and the eigenvector, which is like again very simple. So what we are supposed to do over here is, so if we have to create or if we have to calculate a principal component 1 and if we have to calculate a principal component 2, right? So based on these eigenvalues or based on this eigenvector, so we will be able to calculate a principal component of one column and principal component for a two principal component I will be able to calculate. So let's try to understand how I will be able to calculate, and then we can try to see even a plot summary of the same thing. So here let's try to extract this data and this data. And one more thing. So whenever you are trying to calculate this PC1 and PC2, so you are supposed to check that whether both of these things are orthogonal or not, because it's just representing an axis and angle between an axis must be 90 degree. So you are supposed to check whether these things are orthogonal or not, means there is a 90 degree between these two things or not. You are supposed to check at any point of a time. So no issue, we can try to check each and everything one by one and one by one. We can try to check it. So first of all, let's try to do one thing, right? So here, maybe we can try to calculate sigma times, or sigma is nothing but it's our covariance matrices, right? So if we are going to do this one, so sigma means this matrix multiplication by the matrices that we are able to get out of this one. So this first eigenvector. So if I'm going to extract X of all the rows and a very first column, in that case, this is a value which I'm able to get. This and this I'm trying to multiply with a sigma, means this one. And then if I'm going to multiply this sigma with respect to X of maybe column and 0. So this is the value which I will be able to get. Now, what is the meaning of this value, and why we are even doing these things? So it will be like a 1. Yeah. So what is the meaning of this one and why we are even doing these things? Just try to understand it. So our objective is to find out a very first principal component, right? And our objective is to find out a second principal component. So how I will be able to find out two principal component. So if I have to find out a very first principal component, so the very first principal component is nothing but a component with the biggest eigen value, means biggest lambda value is going to be the very first principal component I will be able to see, or I will be able to get. So here, let's try to multiply this with maybe this one. So it is going to give you a very first principal component, and when you are going to multiply this with this one, so it is going to give you ideally a very second principal component. So here, let's try to do one thing. Let me show you a principal component and a reverse engineering of it. Okay, so here, let's suppose I have x. So x colon all row colon 1, this is a very first principal component. So here we can try to write down in this way. Let me just mark it, print first principal component, and then we can try to maybe print second principal component. Second principal component is which one? A vector with the lowest eigenvalue. So here I can try to extract this one. Okay, it's going to be 0. Yeah. So the very first principal component and second principal component I'm able to find out with the help of this eigenvalue and eigenvector decomposition. And this is again very straightforward. So once you are going to do this eigenvalue, right? So whatever eigenvalues it is going to give you, suppose this one is the maximum one, means lambda value of this one is maximum. So this vector is representing a very first principal component. If this one is maximum, in that case, this will represent a very first principal component. So in this way, we always try to consider. So, okay, this is like completely fine. We don't have any kind of a issue in terms of doing these things. And we are able to find out a very first principal component, and we are able to find out a very second principal component. But the problem is I have this data, right? If you remember, so I had this particular data set. How I will be able to transform this data set? Because my problem is I'm able to find out a principal component, right? So my problem over here is that, let's suppose if this is my data set and I'm able to find out this PC1, but I told you I have to transform this data set, right? And I have to rotate this axis in such a way that it will behave as a x-axis. Then only I can say that it's a first principal component derivation. I'm supposed to represent all of my data set in this axis. So how I will be able to do that? So what I can do is, so if I have to do this kind of a calculation, so I can simply multiply this data set with my, so let's suppose this is my data set, and I can try to multiply this data set with what? With my principal component 1. And what is my principal component 1? So this is my principal component 1 over here. Now this is a value which we are able to receive in this particular place. So here, these are nothing but it's a data which is a transformed one, or this is an array which is a transformed one that we are able to find out. This is one of the column value that we are able to find out. Let's suppose I'm going to store these things into a ARR, right? ARR maybe 1, or maybe PC 1 underscore ARR. So here, and PC1 underscore ARR dot tree. Okay, even without T, it's fine. So this is something that you will be able to get as a very first column transformation, or PC1, the complete PC1 after the transformation. Let's suppose if I have to get a PC2, so in that case, what I will do, so maybe a PC2 underscore ARR is equals to my original data set into a principal component, the smallest one. So X of 0, we can try to calculate. X of all row and 0th column, I can try to calculate. So PC2 ARR is going to give you a second component. So it's the same number wise, number of row wise, you will be able to find out that number of row wise both is exactly same. There is no differences that you will be able to find out of this one. So this is my one of the column, and this is my another column. We can try to even calculate explained variance ratio of this entire data set, and then we can try to perform an operations. We can try to get to know that, okay, fine, so what is a contribution of this PC and what is the contribution of this PC, and easily, yes, we will be able to know about each and everything, which is not at all a big deal in our cases. So here, if I'll try to give you a revision of this entire steps, right? So what we are doing since a very beginning, so we have taken a data set, a simple one. Then we are trying to find out basically a covariances. So first of all, we are trying to check whether data set is normalized or not. Then we are trying to find out a covariances of it. So covariance is always representing a kind of line relations. So this line, now that line, with the help of that line, I'm supposed to find out a vector, eigenvector basically, which by which I will be able to represent my data set into a different scale or into a different axis. I will be able to represent or my vectors. So fine. Once I'm able to find out the covariance matrices, I'll simply try to find out the eigenvalue. Once I will be able to find out eigenvalue, so eigenvalue, the biggest eigenvalue is telling me that it's a first component. A smallest one is telling me that it's a second component. So once it will it will be able to tell me these things, then what I can do, so then I can try to start finding a principal component 1, principal component 2, and so on. So let's try to repeat this entire procedure, and let's try to for one particular data set. So let's try to decompose it, right? So here, what I can do is, so maybe I can try to take numpy dot random dot randn, and or else what I can do is, so maybe I can try to take some other data set itself. So I think I have a glass data set. So let me take some glass data. So let's suppose this is the data set which is given to me. Now in this data set, there are so many columns which is given to you, right? So what I'm supposed to do is, so I'm supposed to do a dimensionality reduction. So let's suppose there are so many columns and I don't know that which column is contributing and which column is not contributing. I don't know about it. So maybe I'm supposed to find out that what is a contribution of each and every columns, or maybe if I have to reduce this so many columns into a couple of columns, I can do that maybe, right? So let's try to run a principal component on this particular one. So let's try to store these things as a data frame. Now this is a data frame that we have. Try to take only feature values, because only for feature values we do a double standard reduction. There is no meaning of doing these things on a label. So if I have to extract a feature value, so what we can do is, so data frame dot maybe a drop, and then we can try to drop basically index column, because index is just a dummy column over here. Index column we can try to drop, and then we can try to drop a class column, right? And this is going to give you basically a new data frame. So this is fine. Key error index and class fine. I believe axis it is not able to identify. Data frame dot drop. Okay, so columns, right? Class not found in the axis. It's C capital. Yeah. So C capital. Now data frame. So yes, this is the data frame that we have. Just try to understand this part first of all, instead of doing it. So for any kind of a data set, you will be able to calculate it manually. I could have used directly a PCA, but that is not an idea. I'll try to use it in a later stage, PCA, right? So here, this is a data set which is given to me. Now, the very first thing that you are supposed to find out over here is that whether an average of all of these data set is 0 or not. And standard deviation of all of these data set is 1 or not. So how I can do that? So maybe data frame dot describe. I can try to call data frame dot describe. So what is an average? So can I say that average of this data frame is not equal to 0? And standard deviation of this data frame or this columns are not equal to 1. Yes. So what is the very first step that I'm supposed to run? So first of all, I'm supposed to convert all of my data set into a standard normal distribution. Can I say that? So no issue. I can try to call sklearn library, and out of my sklearn library, so I can try to convert this data. So out of this sklearn library, so I can try to like call this standard scalar, and then I can try to pass my entire data set inside a standard scalar and then scalar, right? So I can try to basically like call a scalar dot fit transform, and I can try to fit my data frame, and it is going to give me a data frame which can be a scaled one. Okay. So now data frame underscore scaled dot describe, if I'm going to check DSCRIBE, describe if I'm going to check. Okay, so it is available in a form of numpy array. So no issue. I can try to convert these things into a data frame. Pandas dot data frame, and let's convert these things into a data frame, and then we can try to run, right? df1, let's suppose, and then df1 dot we can try to call destroy. So can I say that now my average is 0 and standard deviation is close to 1? Yes, everyone. After doing, mean is not 0, mean is actually 0. It's e to the power minus 14. So it's 0 0 0 0 0 0 0 0 14. It's a very small values, right? So it is tending to actually 0. So you can just check e to the power minus 16, minus 16, minus 17. So just imagine it is actually a 0, and the standard deviation is actually 1 because e to the power 0 0. So anyhow it will be equal to 1. So yes, mean is equal to 0, standard deviation is equals to 1. We are able to achieve. Now, what is our next step that we are supposed to do? Any idea? What is our next step, guys? So can I say that once we have this one, once we are able to do a standard scalar, right? So maybe we can try to find out a line or a relations. This is what we do. First, we shift a data set, then we draw a line, then we rotate it, right? And then we try to find out components. Is it correct? Yes. Yeah. So we have done a shifting part by using a standard scaling, right? Then we will try to find out the relation part by using a covariances. Then we try to rotate it by the help of eigenvalue, eigenvector. And then we will try to find out the principal component. Is it fine to all of you? Yes. So these are the steps. So what we can do over here is that we can try to find out a covariance. So np dot, maybe I can try to write a covariances over here, and covariance of what? So maybe covariance of this one we can try to find out. So this is a covariance matrices that I'm able to find out. So fine, maybe I can try to store these things as a sigma, right? Just like before. So this is a covariance matrices for this n cross n. So we have like so many columns. So n cross n like it is going to give it to me. Now, once this covariance matrices is available to you, then what we are supposed to do? So can I say that we are supposed to find out a eigenvalue and eigenvector? Yes, everyone. So can I say that we are supposed to find out eigenvalue and eigenvector? This one, right? So fine, I'll try to find out eigenvalue and eigenvector by passing this like a covariance matrices over here. So fine, just pass it. So what is my eigenvalues? This one. What is my like eigenvectors? So this one. So I'm able to find out eigenvalues and I'm able to find out a eigenvector out of this one. And here you will be able to find out eigenvalue, eigenvector even in terms of a real and imaginary number. Are you able to see this? So generally when I teach like this imaginary number, right, in my Python classes, so people say that where you are going to use it. See, system itself is giving you this complex number, right? So eigenvalues and eigenvector you will be able to find out, right? Now there are so many eigenvalues and so many eigenvectors I'm like able to get over here. np.lineage.sigma. So what is the, no, actually it is not supposed to give you these many. So it is supposed to give you only like a number of eigenvalue is always equals to the number of like columns that we have. So I think it has already exceeded. And DF scaled fit transformation. So yeah, we are trying to consider this one. DF1 is, yeah, that's fine. So both is same, right? DF1 and that one is like there is no differences. Even last time this mistake has happened with me, I remember in my last class. So a standard scalar is fine. We are like able to do it, right? So after doing a standard scaling, so we are trying to find out this eigen values. So here we are just supposed to pass our sigma, and let's try to understand whether sigma is correct or not. So before that, let's try to draw. This is my df dot scale, right? So I can try to save 214 cross 9. Okay, fine. So 214 cross 9. So it's ideally a 9 column that we have over here. And we can try to like calculate even these things manually. So this dot t matrix multiplication of df underscore scale divided by 214 was the total record, so 213. So this is something that we can try to pass inside this one and then try to observe. Yeah, so there was a mistake in terms of like doing a calculation of this covariance matrices, right? This is giving you the real covariance matrices, right? So this is basically a eigenvalue and this is a eigenvector. This is the eigenvalues and this is the respective eigenvector. I told you, right? Eigenvalue will always be equal to a number of the columns because for every column we are trying to find out the eigenvalues, right? So ideally 9 eigenvalues we are supposed to get, and yes, we are able to get a 9 eigenvalues. Now just tell me, so which one is going to be a PC1? So which one is going to help me to build a principal component one? So see, just try to remember, we have shifted the data set, right? We are able to find out the covariance matrices, means we are able to draw the line, right? Now we are trying to rotate it, right? So once we are trying to rotate it, so how I will be able to rotate? once I will be able to know the rotation means what? Shifting the entire axis. So how I will be able to do that? If I know the value of lambda and the vector, right? So what is our eigenvalues that we are supposed to like, which is going to play a PC1? So people are suggesting that this one is going to play a PC1, but I believe it's having e to the power minus of 1, right? Which one is a bigger one? So 1.6, I believe we have 2.5, even we have 2.52. So 2.52, right? The first one. Can I say that this is going to be the principal component 1? Means which vector I am supposed to select? A very first vector I am supposed to select, right? For the principal component 1. So how I will be able to find out principal component 1 over here? So I will be able to find out a principal component 1 if I am going to, means the like a new column I will be able to derive by multiplying my whole data set by what data set? The corresponding eigenvector of this eigenvalue, right? So what is the corresponding eigenvector? So can I say that this is the corresponding eigenvector? Yes. So I'm supposed to multiply my whole data set. What is the dimension of my data set? So can I say that dimension of my data set is 214 into 9? And then we are trying to multiply with what? So can I say that we are trying to like, we are trying to multiply with 9 cross 1. So 9 cross 1. So can I say that it is going to give me 214 cross 1? So 214 rows and one column. So one column I'm trying to derive out of this entire one, right? Rotation is multiplication with the eigenvector, right? Yes, it's a rotation means multiplication with the eigenvector. So means with respect to this component, this is something called as rotation, that we are trying to rotate it over here. So this is something that I will be able to get. So yes, no issue. So if I have to like calculate a PC1 over here, manual calculation, right? So PC1, if I'm supposed to calculate for a particular data set, then what I will have to do. So original data set, what is my original data set, by the way? So my original data set is this scaled data set. So data frame dot scaled, right? Data set frame dot scaled into matrix multiplication I'm supposed to do, right? So x of all row, zeroth column. So x of all row and zeroth column, okay? So this is going to become a PC1 for me. So 214. What is the total number of values? If you will try to check a shape of it, right? So can I say that it's a 214 cross 1? Yes. So principal component 1 data means very one principal component I am able to derive. Similarly, so I will be able to derive what? So I will be able to derive a principal component 2, right? Principal component 2. So if I have to derive principal component 2, no issue. So how I will be able to get a principal component 2? So which one is the second highest? So can I say that second highest is this one? Yes. Third highest is this one. Fourth highest is this one. Yes. So fine, this one, and this is going to give me second principal component, second column values it is going to give me. So this is the transformed data I'm able to get for a first principal component, second principal component. So I will be able to get all of these data set for all the principal components. So even if I have like a hundreds of principal components, so I will be able to get the same data. Now I have to validate, right? Now I have to validate that whatever operations we are doing, so is it aligned with the reality, aligned with a reality or not, right? Let's suppose we have to validate that particular part as well. So see, we are able to generate principal component 1, 2, 3, 4 till 9 we will be able to generate. There is no issue with that, right? Easily we all can calculate it. But whether this principal component is correct or not, how I will be able to validate? So there is one way. This two principal components should be orthogonal to each other. Orthogonal is perpendicular. So matrix multiplication of a perpendicular vector is equal to 0. So that is one of the way, right? Another way is, so maybe I can try to do a reverse engineering. So see, when we are trying to generate a principal component, when we are trying to derive a data set with respect to a principal component, so can I say at that point of a time that we are actually trying to scatter a component of a data set in, because data set in any free space is a component of a respective coordinates or respective axis at any point of a time. So can I say that by using, if suppose if we have derived the data set, so by using a reverse engineering, if we will be able to recreate a data set, then also I will be able to prove. Recreate means original data set I'm talking about. So if I will be able to recreate this original data set, so can I say that even I will be able to prove it? So there are multiple ways by which I will be able to create, or maybe I will be able to prove or disapprove myself. There is no issue, right? So what we can do is, so maybe one of the simplest way we can try to apply, and we can try to find out a principal component with the help of scikit-learn library, and then we can try to check so whether our value that we are calculating manually is equivalent to a value that has been calculated by library or not. So from sklearn, just for the validation purpose, decomposition. So inside a decomposition class, this is available. So import basically what? So import basically PCA, right? Okay. So try to create an object of a PCA, by the way, right? Okay, it's a small PCA. Try to model object not callable. Why it is not callable? This one is PCA. PCA. Fine. So this is the principal component analysis that I'm able to see. Now here, so it is like this algorithm is asking you number of components. So for how many components you are trying to call or calculate the PCA. So that is completely fine. I will just try to pass my original data set, right? I'll try to pass my original data set, and then I will try to generate this principal component at any point of time. So here, maybe I can try to write down that, or I can try to fit in my data set, and I can try to set number of component is equals to 2. 2 PCA we have calculated, right? So we just have to match with these two, right? So whether our PCA values and PCA values from here is correct or not. So let's suppose I'm generating a 2 principal component, right? So 2 principal component, if I have to generate over here, so I can try to call PCA dot fit transform, right? And what kind of a data we are going to pass? So this data we can try to pass same one. So everything will be done by internal things. So these are the values. One, so the very first principal component is this one, and the second principal component is this one. Very first principal component value is what? And let me just try to print it. PC1. What is the variable name? So PC1 data. Yeah. So PC1 data. 1.15, 5.74, 9.40, 1.15, 5.74, 9.40, 1. Just look after the value. Forget about the vector. It's a reverse sign that we are able to get because we have to do a transpose over there. But can I say that we are able to get exact same values while we were trying to do a principal a component manually? So when we have find out the covariance matrices, and then we have done the eigenvalue decomposition. Yes. So is it, are we able to get the same values? Yeah, we are able to get the same values. Now, so let's suppose I have 9 PC, mainly 9 PC I will be able to generate, right, in total. But like I asked you a question even before that, let's suppose there are 100 columns, and out of 100 columns, if I have to select maybe 2 columns or maybe 3 columns, right? So how I will be able to select these 2 columns or 3 columns, or how many columns or how many PCs we are supposed to select, right? How I will get to know. So how I will be able to know that? So again, I will be able to know that with the help of screen plot, and screen plot can be done with the help of EVR, explained variance ratio. So see here we have these many data set, right? Means we have total like in total, if I'll talk about a df1, so we have 9 total number of columns. So 9 pc we will be able to generate, right? But how many values or how many columns, how many pcs, principal components, will be able to explain the whole data? How I will get to know about that one? So let's try to understand that particular part. So we talked about explain variance ratio, we talked about screen plot, right? So we are going to do the same thing over here. So we can try to do create maybe PCA, right? And this time, so we are not going to define the number of component. So we can try to call dot PCA dot fit transform over here, and we can try to pass data frame 1. So fine, it is able to transform this entire data set, and this is called as principal underscore component. So fine, these are the principal component which I'm able to find out. So all the 9 principal components I'm able to find out. Now I can try to call plt dot maybe a figure, plt dot a figure over here, and here separately I would like to show you that principal component dot or this PCA dot explained variance ratio. Now this is the explained variance ratio that we are able to get, right? This is the explained variance ratio I'm able to get for 0, for 1, for 2, for 3, for 4, for 6, 7, 8, and 9, and all. So this is the explained variance ratio that we all are able to achieve. Now let's try to do one thing. So maybe let's try to like plot this one, right? So if I have to plot, so maybe come some I can try to use plt dot plot so that I will be able to consume the entire axis. So come sum, cumulative sum, and then PCA, this one. So we can try to plot it. PLT is not defined. Okay. Import plot matplotlib dot pyplot as PLT. Yeah. So this is something called as screen plot, right? So here on your x-axis, you will be able to find out, right? So what I'm trying to do, I'm just trying to like, I have just printed this one, right? Index wise, and then I'm just trying to like plot it. So plt dot plot and explain variance ratio. So this is the explain variance ratio in between 0 to 1. Come some I have done because every time, so it will be like on an axis, it is supposed to like a adds on, and then combination of this entire things is equals to 1. Explain variance ratio is equal to 1. If you remember, 0.91 plus 0.09 is equals to 1. So in the similar way, that's the reason so I have used come sum, because it is going to give you just 0.91. So here, right? So here we are able to do a screen plot. Maybe if you are looking for a labels or something, so I can try to do that as well. So plt dot xlabel x label, and then we can try to keep it as a number of required component, right? And then here, so maybe plt dot y la label. So here EVR, explained variance ratio or variance of the data set, right? So this is what it is representing. Now, if I'll ask you a question, look into this graph, right? And tell me that how many components are actually required to explain my data set, maybe more than 90%. So maybe 5 or 6, right? So 5 or 6 number of component if I'm going to utilize, means I have total 9 columns, but finally if I'm going to create a 5 PCs, right? 5 PCs if I'm able to create, so can I say that I will be able to get a whole meaning of the data set, or more than 90% meaning of the data set I will be able to get? Yes. So this is something called as a screen plot. Yes. And explained variance ratio, this is how we are able to find out. Even you can do a manual calculation for explained variance ratios in a easiest possible way, and you will be able to find out the same thing. Even manually you will be able to calculate all the principal components, like we were able to do like a pc1, pc2, pc3, each and everything we were able to do it. So in the similar way, even you will be able to do this kind of operations. So it's completely fine. I think it's a time, so I'll just like show you one thing. So I have to discuss more things in this PC. So with respect to a data set, so I have just like given you a simple explanation of this one. Now just try to understand this and just look into this picture and tell me whether we were trying to discuss a same thing or not. Just try to focus on this line, and when this line is going to cross this pink line, right? So can I say that at that point of a time, it is going to show you the maximum covariances? Yes, just now, right? It has shown you the covariances, and there will be another light black line you will be able to find out over here, right? Which is representing what? This black line. This black line. So this is representing what? So this is basically representing the another component over here. So I have a data set, right? This is a normalized, this is the standardized data set that we have. And what we are trying to do, so we are just trying to find out the best fitted line, and then that lines we are trying to convert into a now principal component. See, when this is going to overlap with the x-axis and like a y-axis. So this is something that you will be able to do, right? So this rotations of the data set is possible based out of what? Eigenvector and eigenvalues, because this vector we are trying to represent in another way. Now here, so in next class, I have to discuss this all of these examples with you. So where I will try to show you that, let's suppose if I have images, right? Whenever you will try to take images, so at that point of a time, right? So at that point of a time, what happens? Let's suppose if you have taken your pictures, right? Or maybe in my system, if I have some pictures, because principal component is again a kind of a technique which has been used widely with respect to pictures. So fine, let's suppose I have this picture, right? I have this particular picture. Now if I'll just right click, and then if I'll try to check a properties over here, so you will be able to find out that picture size is 428 into 317. This is the pixel size, right? What is the meaning of it? So can I say that meaning of this one is nothing but 428 row and 317 number of columns. Someone is saying that 428 features. No, 317 feature, right? Feature is column. Okay. So 428 rows into columns, and 317 number of columns. That is representing one single picture. So whenever we face challenges with a training of this entire convolutional neural network, or whenever we see that, okay, fine, so because even in neural network, when I will teach you, or maybe Sunny is going to teach you, so you will be able to understand that it's nothing but just try to understand a relationship between your data values. Data values means your like a numerical values, pixels numerical values. That's it, right? So what we can try, we always do is, so we always try to do a principal component analysis. Why to take 317 columns, right? Maybe there is a possibility that I will be able to explain this entire images just with the help of 50 columns, 50 pixels. Possible, right? If you are going to say yes, if you are going to say no, that is also fine, because I'll show you, right? So how one picture I will take, maybe even your picture I can take immediately, and then like I'll try to show you, or I'll try to represent your pictures just with the help of like instead of representing this picture into a very high dimension. High dimension means number of pixels, we try to say that, right? So like pixels is HD quality. HD quality means what? It like a 1080p generally we try to say, or we say 4K, right? So it simply means that number of rows and columns are more over there in a smaller space. That is the only meaning. But that doesn't mean that I need that many number of the columns for the representation. I can use even a lower volume. So whenever like a system, our system struggles to like learn on new things, on new features with the help, because if number of features are increasing, it simply means that you are increasing the complexity of a relationship, right? And system will face a difficulties to learn, as I have highlighted in a very first place when I started my lecture on PCA. So what we do is we just try to decompose it, right? We say that, okay, fine. So why to use a 317 number of columns that I have shown you, right, in a pictures? Instead of that, maybe I can use just 30, right? So image compression technology uses that. There are many more technologies you will be able to find out. This is just one of those I'm trying to discuss over here, so that my machine will be able to like face a less challenges. Because at the end of the day, whether it's a machine learning, whether it's a neural network, it is trying to find out the pattern, right? It is just trying to find out the pattern. Nothing else it is trying to find out except a pattern. And in a beautiful way, it will be able to find out the pattern if relationship is less complex. If relationship will, when relationship will less complex, when feature is less. So what we do is just decrease it. So PCA is used for the feature selection. No, not at all. You are incorrect. So feature PCA is used for feature decomposition, not for the feature selection, right? So feature selection, we generally like do it with the help of like a business. So we discuss these things with the business. We understand each and every values and the significance of the column, and then the rotational apart. Okay, so that will be discussed. So fine, in our like upcoming classes, I will be like talking about all of these things, right? Which I have already discussed even in my previous classes. So I'll try to show you that when we take one image, right? And just try to imagine this is a 64 cross 64 images we have taken. Just try to look into this image. This is 64 cross 64 images we have taken. So are you able to understand what is a digit it is representing? 0, right? Okay. So it is basically representing a 0. Now just tell me, here we have just taken, so in this n is equal to 1. So here we have just, I'll show you, I'll run this example, I'll show it to you. But here we have taken just one principal component. Are you able to understand this digit? Probably no, right? Here we have taken two principal component, means just two axes of this one. Are you able to understand these images? Better, right? Better than the before. Here 3, little bit better. Can I say that? Right? More variances I'm able to explain, more variances I'm trying to add, right? By the time I'll come to this 4, right, I believe we all will be, or 5 or maybe 6 or max to max 8, I believe we all will be able to understand what. So we all will be able to understand a principle, like we all will be able to understand the actual digits. So if we are able to understand our data set, pattern of this data set at this point of a time itself with 8 dimension, right? Why to take 64 dimension then? Are you able to understand this significance of PCA? So when we are able to derive our data set, because see, even image is just a data set, just a pixels, rows and columns, nothing else. You can just right click on your images and you will be able to see this X cross Y or row cross columns, right? Actually, it's a values. Every pixel is having a values. If you will open up your images in a paint, right? I think Microsoft Paint, you all are aware about it. If you hover your mouse in your like a left hand side corner, you will be able to see even a pixel values with the coordinate values, right? So here, when there is a data set which we can like derive, or which I will be, because at the end of the day, it's just whether it's a human or whether it's a machine learning algorithm or deep learning algorithm, what we are trying to do, we are just trying to understand the pattern. If I'm able to understand this 0, my work is done. Next time I will be able to recognize, right? So if I'm able to understand these things with the 8 dimension, why to give 64 dimension then? Yes. So that is a major advantage. So PCA is not a machine learning algorithm. It's just a way by which you will be able to prepare your data set, right? So PCA is not an algorithm which has been used for building a model, not at all. Don't go in an interview and say that, okay, I have used a PCA to build a model. So PCA is not an algorithm which has been used to build a model. It's basically a procedure by which you will be able to recreate the data set, right? So this is where PCA comes into a picture. And going forward, so that's the reason, so I haven't discussed my other algorithms. So going forward, almost in all the algorithms, instead of taking all the columns, what I will do is I will start using PCA, right? I'll start using PCA. So XGBoost I have to discuss, or other algorithms I have to discuss. What I will do is I'll start using PCAs everywhere, right? And then with PCA, without PCA, we can try to check a result plus stability of the model. I believe in decision tree we have already discussed about it, right? What is called as stability of the model? How to bring PCA data into original data? I'll show you next time. It's actually very, very simple. So if you remember, we have multiplied these things with the eigenvector, right? Like whole data into a eigenvector of like a highest PCA, then lowest one, then its lowest one. So what we can do is, so like a the result that we are able to get, transpose of that into a eigenvector, a summation of the whole data set. I'll show you, and you will be able to find out that we are able to regenerate the actual data set. It simply means, right? It simply means that even after doing a PCA, we are not losing a meaning of it, right? So just it's just a 1 or 2 minute it will take for me. So when I'll discuss about the PCAs, so yes, and when I will be using a PCS with respect to other algorithms, so at that point of a time, I'll try to explain you. So implementation wise, it's very easy, right? Simple. Call a standard scalar, standardize the data set, right? Try to compute a covariances, then eigenvector, eigenvalues. So based on the highest eigenvalues, choose your first PCA, multiply with the data set generated, right? And in terms of visualization, if you have to do, so simple, take a data set, shift it, draw the line, right? Rotate it. Today is my great class. Yes. So visualization wise as well as programmatically, we all will be able to calculate, right? So scale-learn PC algorithm internally is scaled all the data set. Yeah, you can just try to check like what they are doing internally, but yeah, it does that. Sklearn has already taken all the pain of the computation. Yeah, Sklearn has already taken all the pain of the computation, but we should know, right, what is happening internally. So when we are talking about the PCA, so it's not an elimination strategy, it's basically a reduction strategy that we are trying to help. Ajit is asking, in case of customer segmentation, say we have 100 columns, doing a PCA is a good decision, but we will not know the original column name. Yeah, so I'll show you that next time. When you do a PCA, right, so you lose your original column name by default. Because see, PCA is not a original column. Guys, are you able to understand it? So we are not able to retain the original column name even. It's a new column that we are trying to derive, which is where in one column, let's suppose if I'm trying to derive a principal component first column, so basically that first column is a combination of all the columns. Can I say that? It's basically a combination, because every component is contributing over there, right? So let's suppose if I'm going to show you again this one. So see here, if this is like a data set that we have, right? And if this is the line which I'm trying to draw, let's suppose I'm trying to say this things as a PC1 and this things as a PC2, right? So whatever data that we are representing over here, right? Whatever data, so can I say that this data set is representing two column? It's available in 2D, right? It's represented two column, right? So we are taking a component of both the columns over here. That's the reason. So when we were trying to find out the eigenvector, right? So we have multiplied with the whole data set, right? So it's a whole component that we are trying to take. So we are actually trying to derive a new column out of the whole column, all the existing column. In regression, we are trying to drop a column with the covariances, but in PCA, covariance is necessary. See, in regression, we were trying to find out a relationship between X and Y. So if there is a relationship between X and X, that creates a multicollinearity and which nullifies your actual learning with Y. That is the reason, right? But here, so have we considered even a y over here label? No, right? We have just considered what? Features. In case of PCA, we have just considered the feature part, right? So it's just a column to column relations that we are like worried about over here. Apart from this, so we are not even concerned of like any other things. So yes, so rotation or lambda multiplication correlation is still not fully understand. Rotation and lambda multiplication. Fine, maybe next class you can, or just try to watch one more time. It will be clear. PCA is unsupervised learning. See, it's not even a learning. How it is learning? Tell me. Do we have any like a parameter which we are trying to train over here? Guys, anyone? Are we learning something in PCA? I told you, right? It's not a machine learning algorithm. It's basically an algorithm which helps you out to perform your like a data selection. We are not learning anything, right? We're just doing a straightforward calculation. We are not learning anything over here. PCA is just a technique by which you will be able to reduce a dimension of the data set. So it is a technique which helps you out for a data preparation. Okay, so standard scalar concept, is it a learning algorithm? Standard scaling we call again and again, right? No, right? Similarly, PCA, it's a technique, right? This is where people get confused. People think that PCA is a learning algorithm. It's not in actual. So many people say that it's a learning algorithm, but no, that's not like that. What is your prediction on India versus Pak match? See, I told you, right? So I don't know about cricket. So a person like me will start giving a prediction in that case. Yeah. So how user will enter data when we build the web app using a PCA, because column will left by default. I'll show you. I'll show you those things. A prediction part. Anyhow, I have not shown you, right? So that's the reason I told you that I'll try to use PCA with algorithm now, right? Not PCA standalone, because standalone means what? I'm just decompose the data set. Then what? Yeah. So when I will try to use a PCA with an algorithm, right? Then you will be able to understand how, if we have used a PCA, then how prediction is going to happen. So PCA with algorithm, I'll try to use next time, immediately in your next class itself. Is class over today? Yeah, you can go and watch your match. So that's fine. You must be missing your match. So I'm really very sorry for extending your classes. Yeah. So fine, guys. Go and watch, right, your matches. Okay, someone is saying that it will start by 7. Yeah, then we have a time, right? Okay, so maybe people are looking for some extra time so that they can go and arrange some snacks or something. Okay, is it going to start from 7:30 or 7? Because I'm not aware about the timing. So literally, so it's like my class is again scheduled from 8 like PM IST. So PCA is just to facilitate the ML algo so that time complexity is not compromised, even though more number of columns are considered. Yeah, that is one of the like that is one of the reason. Apart from that, there is other reasons. 4 reasons I have written, I believe, right? So yeah, explanation is amazing. Thank you. What sports you are fond of? Actually, I don't play any kind of sports. I don't even know. So see, sometime I like play maybe volleyball, and I don't know like when I have played last time, maybe 5, 6, 8 years back, and still I used to say I used to play a volleyball maybe 8 years back, and sometime it's like chess. I say that I'm good with chess, but again, it's been more than 2 to 3 years since I have played chess. Even I have touched chessboard, right? Although I'm good with it, but still. And so I don't know, like game wise. So when you run a startup, right? So you barely get a time for anything else. When you just like engage into something for day and night. So it's better to like what I always think is it's better to work hard for maybe some time or maybe for a couple of years instead of working hard for an entire life till 60 years till your retirement. So I'm a person who believes in this particular like a fact, and maybe because of that I'm just like working. Yeah. So and generally I used to give advice to everyone that just work hard, everything is possible in this world, nothing is impossible, right? It's not like you are going to be the first example or anyone else is going to be the first example. We have so many examples. right? Things are not tough at all, just hard work, no shortcut. Dedications, honesty is very, very important. You are not supposed to be honest with others. Actually, you are supposed to be honest with yourself in a very first place. Then everything will happen in time. सर, आपका फर्स्ट करवा चौथ है, आप भी टाइम से लीव ले लो. अच्छा, ऐसा है क्या? करवा चौथ है? आई डोंट नो अबाउट दिस, लाइक मे बी. Can you show PC5? Don't worry, I'll take 100 columns. I'll show you PC100 as well. And same thing, I can prove it with the manually. I'll calculate PC100, and same thing I'll show you with the like a principal component a PCA with scikit-learn. Both I'll show you, manual plus in automated way. 8 नियम वालों की लग गई इंडिया पाकिस्तान मैच वर्सेस डेटा साइंस वर्सेस करवा. Yeah, for sake. Okay. So Ellen must be पीछे छोड़ने वाले हैं. नहीं नहीं, he is already like on the level, so it's not that like easy or possible. See, we all have our own line and length, right? We should not compare with anyone. No one knows what will happen tomorrow, right? So we should not compare, just we should work. And yes, you will like you will see an outcome. If you're working, for sure you will see the outcome. Believe me, I have seen these things, right? If you're working, so yes, outcome will be visible, very, very clearly visible to you. So just do that. Instant outcome, maybe you will not be able to get, but yes, 1 or 2 months may change many things in your life. And 1 year or 5 years will change everything in your life for 60 years. And not just for you and your life, for your entire family. Sir, it's matter number of PCA is equals to number of columns. Yeah, number of PCA is going to be a number of column by default, because that is the number of component it is going to generate, right? Because for every columns, but it depends upon us based on EVR, explained variance ratio, that how many PCA we are going to select, right? Okay. So fine, guys, thank you so much. See you again on Saturday. Please do revise a concept which I have discussed, right? So far, so forth. Next week, I believe both of these days is going to be a back-to-back practical session, because we have discussed so many theoretical things, but we are yet to do a practical. So it will be a back-to-back practical. Be ready with it. Yeah. And before that, just make sure theory is important, so that you all will be able to correlate and recall, right? And hope you are working on projectathon, and I'm assuming that you all are working on this one. Yesterday I have given you this question, right? So actually I have given you this question like a couple of months back, but I have seen some of the article. I think 1 or 2 article I have seen on in blog, right? I was just going through it. I have seen that like yes, people have started working on it. Even you can go and check in blog. Okay, Sunny is saying it's working. Thank you. Thanks. Yeah. So fine, guys. Thank you so much. See you again in your next session. Yeah. Thanks. Bye, everyone.